What if the universe we know is only a fraction of a much stranger, more complex reality? Beyond the known boundaries of space and time lies a realm filled with anomalies that challenge our understanding of the cosmos. These cosmic disturbances, from erratic stellar behaviors to peculiar galaxies, reveal the mysteries lurking just outside what we can comprehend. Dark matter is one of the most intriguing mysteries of modern cosmology, and its existence has been inferred from several compelling pieces of evidence. The first and perhaps most striking piece comes from the observation of galaxies. When astronomers look at how galaxies rotate, they notice that the outer edges spin much faster than they should, based on the visible matter alone. This discrepancy suggests that there is some unseen mass exerting gravitational influence. This unseen mass is what we call dark matter. Another strong indicator of dark matter is the way light bends around massive objects, known as gravitational lensing. When a massive galaxy or cluster of galaxies lies between us and a more distant light source, it can distort and amplify that light. The degree of bending allows scientists to calculate the mass of the foreground object. Observations show that the mass required to create the lensing effects exceeds what we can see with telescopes, suggesting that there is much more mass present, which again points to dark matter. Theories surrounding dark matter propose that it is made up of particles that do not interact with electromagnetic forces, meaning they do not emit, absorb, or reflect light. This renders dark matter invisible, making it difficult to directly detect. The leading candidates for dark matter particles include weakly interacting massive particles, or WIMPs. Although numerous experiments are in search of these elusive particles so far, they have yet to be conclusively detected. This invisibility is a significant factor in why dark matter is considered a cosmic anomaly. As for its role in the universe, dark matter affects the formation and structure of galaxies. It acts as a scaffolding around which visible matter clusters, influencing where galaxies form and how they evolve. Without dark matter, the universe as we know it would look dramatically different. We would have fewer galaxies, and the vast cosmic web structure we observe today would not exist. This fundamental aspect of dark matter makes it a critical focus of cosmological research as scientists strive to understand this cosmic enigma and its implications for the universe's history and behavior. Gravitational waves are ripples in the fabric of space and time, generated by the most violent and energetic events in the universe, such as colliding black holes and exploding stars. Their discovery has opened a new chapter in our understanding of the cosmos, one that challenges traditional notions of how we perceive gravity and the nature of the universe itself. When these waves travel through space, they carry with them information about their cataclysmic origins, offering insights into cosmic events that were previously invisible to us. One of the fundamental ways gravitational waves challenge our understanding is by providing evidence for Einstein's theory of general relativity, which posits that gravity is a curvature of space and time caused by mass. The detection of these waves supports the concept that massive objects affect their surroundings, creating waves that spread out through the cosmos. This realization shifts our perception of gravity from a force acting at a distance to a dynamic interaction that shapes the fabric of the universe itself. Furthermore, the study of gravitational waves has highlighted the interconnectedness of space and time, reinforcing the idea that they are not separate entities, but part of a single four-dimensional continuum known as space-time. This understanding prompts us to reconsider how we think about events in the universe. Instead of observing the universe as a static backdrop, we now recognize that it is a living entity, constantly influenced by the activities of its masses. Each gravitational wave carries a unique signature of the event that created it, challenging us to decode the history of the universe in ways we never imagined. As we delve deeper into gravitational wave astronomy, we are not just listening to the echoes of the universe. We are also questioning our fundamental grasp of reality itself. Each detection can unravel new layers of complexity in our understanding of phenomena like black holes and neutron stars, enriching our knowledge while also showing us how much we have yet to learn about the vast, mysterious cosmos in which we reside. Gamma-ray bursts are among the most powerful and energetic events in the universe, releasing immense amounts of energy in a fraction of a second. They are typically caused by massive stars collapsing under their own gravity, leading to a supernova explosion. This collapse creates a black hole or neutron star, resulting in jets of highly energetic particles streaming outward at nearly the speed of light. When these jets point directly toward Earth, we can detect the gamma rays they emit, which can last from milliseconds to several minutes. These bursts can outshine entire galaxies for a brief moment, making them detectable across great distances. The energy released in a single gamma-ray burst can be equivalent to that produced by our Sun over its entire lifetime. This incredible intensity offers a unique window into the violent processes that occur in the universe and helps scientists understand the conditions that lead to the formation of black holes and neutron stars. With their ability to illuminate the distant corners of the universe, gamma-ray bursts also serve as indicators of the early conditions in the cosmos. They are associated with the formation of the first stars and galaxies, allowing astronomers to piece together a timeline of cosmic history. Understanding their origins helps shed light on the fundamental nature of stellar evolution and the cataclysmic events that sculpt our universe. Moreover, studying gamma-ray bursts has broader implications for our understanding of cosmic radiation and the mysterious dark matter that may permeate the universe. Each burst provides a unique opportunity to explore questions about the creation of elements during these explosive events, which in turn influences the formation of new stars and the development of galaxies. Thus, gamma-ray bursts not only mark points of destruction, but are vital milestones in the ongoing story of cosmic evolution. Fast radio bursts, often abbreviated as FRBs, have captured the attention of astronomers and astrophysicists since their first discovery in 2007. These mysterious phenomena are incredibly brief yet powerful bursts of radio waves, lasting just a few milliseconds. They can release as much energy in one pulse as the Sun does in an entire year. Initially, their origins were unknown, but scientists have made significant strides in understanding them, even tracing some bursts back to specific galaxies millions of light-years away. One of the most intriguing aspects of FRBs is their potential sources. While many remain unidentified, some have been linked to highly energetic astrophysical events, such as magnetars, neutron stars with exceptionally strong magnetic fields. Others are still enigmatic, leading researchers to ponder whether they might be manifestations of previously unknown astronomical processes. This uncertainty sparks a wealth of questions about the universe. Are these bursts signaling the presence of advanced extraterrestrial civilizations, or could they be connected to phenomena we have yet to comprehend? Furthermore, fast radio bursts illuminate the complexities of cosmic signals and the interstellar medium. As these radio waves travel across vast distances, they encounter various particles and magnetic fields which alter their frequencies. This phenomenon allows scientists to glean information about the medium they traverse, potentially revealing new insights into the distribution of matter in the universe. Each fast radio burst serves not only as a cosmic enigma, but also as a tool for investigating the structure and behavior of the universe itself. As we continue to study fast radio bursts, our understanding evolves, raising profound questions about the nature of the cosmos. What is the significance of these massive cosmic signals? Are they a mere curiosity, or do they hold the keys to unlocking deeper truths about the universe? With each discovery, we inch closer to unraveling the mysteries of these captivating bursts, reminding us of the vastness and wonder of our universe. Cosmic voids, those vast, nearly empty regions of space, play a significant role in shaping the large-scale structure of our universe. These voids are interspersed among filaments and clusters of galaxies, making up the large-scale web-like structure we observe. While they might seem like nothingness, they actually influence the distribution of matter, guiding how galaxies form and evolve. Their presence helps inform our understanding of the universe's expansion and the distribution of dark matter, which remains shrouded in mystery. As we peer deeper into these cosmic voids, we find intriguing patterns. The galaxies that reside at the edges of these voids tend to move toward denser areas, drawn by the gravitational pull of nearby matter. This movement sparks curiosity about the forces at play within these seemingly empty spaces. Scientists have also noted that these voids can be surprisingly large, with some spanning hundreds of millions of light-years, a scale that challenges our understanding of cosmic dynamics. yet cosmic voids are not fully understood. One lingering question is how they formed in the first place. Current theories suggest that they may have originated from the very early universe, when density fluctuations led to the attraction of matter in certain regions, while leaving others nearly empty. Still, researchers continue to explore whether other factors, such as dark energy or the influence of gravity from neighboring structures, contribute to their development. Moreover, the role of cosmic voids in the overall fate of the universe remains a topic of investigation. Some scientists propose that voids could impact future cosmic evolution, possibly influencing how galaxies and dark matter will behave as the universe continues to expand. Understanding cosmic voids may ultimately unlock secrets about the nature of dark energy, the force behind that expansion, and how it shapes our cosmic landscape. As we uncover these mysteries, we gain deeper insights into the very fabric of our universe. Rogue planets are intriguing celestial bodies that wander through the vast darkness of space without being tethered to a star. Unlike traditional planets that orbit a sun, these nomadic worlds are often ejected from their original solar systems due to gravitational interactions, leaving them adrift in the cold, empty expanse of the universe. Estimates suggest there could be as many rogue planets as there are stars in our galaxy, making them an abundant yet elusive part of our cosmic neighborhood. The significance of rogue planets in the search for extraterrestrial life lies in their potential to host conditions suitable for life. While these planets lack the warmth and light of a star, some may possess geothermal heat from their interior or have trapped heat through the gravitational forces at play. It is hypothesized that these planets could maintain underground oceans or other environments that sustain life, allowing organisms to thrive in unexpected conditions. This concept broadens our understanding of where we might find life beyond Earth. Furthermore, the study of rogue planets challenges the traditional notion of habitable zones or regions around stars where life might exist. If these planets can harbor life despite their isolation, it opens up exciting possibilities for where scientists might search next. For instance, examining planets not bound to stars encourages exploration of diverse environments that might mimic the early Earth's conditions, or reveal life forms adapted to extreme environments elsewhere. Rogue planets serve as reminders of the universe's complexity and mystery. They illuminate the possibilities that life could exist in forms and locations we have yet to fully imagine. As we continue to probe the cosmos, these solitary wanderers will undoubtedly shift our perspective on the potential for life beyond our solar system, enriching our understanding of the universe and our place within it. Black holes are among the most enigmatic objects in the universe, challenging our understanding of physics in fascinating ways. At their core, these regions of space possess gravitational forces so powerful that nothing, not even light, can escape once it crosses a threshold called the event horizon. This unique property makes them difficult to study, as they effectively swallow all information about the material that falls into them, leaving only their mass and spin as observable traits. One way in which black holes defy conventional physics is through their singularities. A singularity is a point at which the laws of physics as we know them break down, with density becoming infinitely large and space-time curving infinitely. This presents a paradox for scientists, as the predictions of general relativity, which describes gravity, clash with those of quantum mechanics, the framework for understanding subatomic particles. The reconciliation of these two theories is one of the greatest challenges in modern physics and hints at fundamental truths about our universe. Moreover, black holes are potential windows into understanding the very fabric of space-time. They may help unravel mysteries related to gravity, the nature of time, and even the possibility of other dimensions. For example, the study of black holes has brought forth concepts like Hawking radiation, proposed by physicist Stephen Hawking, suggesting that black holes can emit radiation and eventually evaporate, leading to questions about their ultimate fate and the information paradox that arises from it. These cosmic giants hold secrets about the early universe, how stars evolve, and even the ultimate destiny of galaxies. As scientists continue to observe black holes, particularly supermassive ones at the centers of galaxies, we inch closer to understanding their role in shaping not just our universe's structure, but also the fundamental laws that govern it. Their mysteries beckon us to delve deeper, reminding us of the rich complexities woven into the cosmos, waiting for us to uncover their secrets. The Shapley supercluster is a massive concentration of galaxies located about 600 million light-years away from Earth, and it's one of the largest structures in our observable universe. The intriguing aspect of the Shapley supercluster lies not only in its sheer size, containing thousands of galaxies, but also in the gravitational forces that govern its dynamic nature. This collection of galaxies and galaxy clusters reveals significant insights about the overall structure of the universe and the forces at play in shaping it. One of the prominent theories surrounding the Shapley supercluster is related to its role within the cosmic web, a vast structure composed of filaments of galaxies and dark matter. Scientists believe that the Shapley supercluster is situated at a critical junction in this web, acting as a gravitational anchor that influences the motion and distribution of nearby galaxy clusters. This position allows astronomers to study how gravitational interactions between clusters can affect the evolution of galaxies, shedding light on processes like galaxy formation and the growth of cosmic structures. As astronomers delve deeper into understanding the Shapley supercluster, they are also confronted with questions about dark matter. Dark matter, which makes up approximately 24% of the universe, cannot be seen directly but exerts gravitational influence on visible matter. The Shapley supercluster provides a unique laboratory for studying this elusive component, as the clusters within it exhibit gravitational effects that can help researchers trace the distribution of dark matter across the universe. Moreover, the Shapley supercluster poses questions about the expansion of the universe itself. Different observational data suggest that structures like the Shapley supercluster might play a role in the localization of the universe's expansion rate. By analyzing the properties and behaviors of the galaxies within this supercluster, astronomers continue to refine their models, enhancing our understanding of cosmic evolution. Thus, the Shapley supercluster stands as a beacon of exploration, inviting scientists to untangle the mysteries of our universe. Neutron stars are one of the most fascinating remnants of stellar evolution. Formed when a massive star exhausts its nuclear fuel and undergoes a supernova explosion, these compact objects are incredibly dense. Just imagine a star whose core has collapsed under gravity into a sphere with a radius of only about 12 miles, yet contains more mass than our entire Sun. This extraordinary compression results in an object where a sugar cube-sized amount of neutron star material would weigh as much as an entire mountain. What's particularly intriguing about neutron stars is their composition. After the supernova, the core collapses, creating conditions so extreme that protons and electrons merge to form neutrons. This means they are primarily composed of these neutrons, tightly packed together. As a consequence, neutron stars have enormous gravitational fields, far surpassing what we experience on Earth. This pressure leads to the formation of a crust made of atomic nuclei, while the interior consists mostly of superfluid neutrons, creating a state of matter not found anywhere else in the universe. Another extraordinary phenomenon associated with neutron stars is their magnetic field. They often possess magnetic fields that are billions of times stronger than Earth's, leading to intense electromagnetic radiation. Some neutron stars rotate at extraordinarily high speeds. Some spin hundreds or even thousands of times per second. This rapid rotation, coupled with their strong magnetic fields, can create beams of radiation, making them appear like cosmic lighthouses. These are known as pulsars, and as they rotate, they emit beams of light that sweep across space. If one of these beams happens to point toward Earth, we observe regular pulses of light. Additionally, neutron stars can exhibit other captivating phenomena. For example, when they are part of a binary system, they can pull material from a companion star. This process can create X-ray bursts, identifiable as bright flashes in the X-ray spectrum. This careful dance between two stars showcases not only their gravitational pull, but also the remarkable interactions that occur in the universe. Indeed, neutron stars serve as a testament to the extremes of nature, providing scientists with insights into fundamental physics that cannot be replicated in laboratories here on Earth. Pulsars are fascinating celestial objects that are a product of the deceased massive stars known as supernovae. When these stars reach the end of their life cycles, they explode spectacularly, leaving behind an incredibly dense core. This core is what we call a neutron star. and pulsars represent a particular type of neutron star that emits beams of electromagnetic radiation from their magnetic poles. As the star spins, often at astonishing rates, these beams sweep through space like a lighthouse beacon, creating regular bursts of radiation that we can detect from Earth. What makes pulsars intriguing is not just their unique properties, but the insights they provide into the life cycles of stars. Traditionally, when we think about stellar evolution, we imagine a star progressing through various stages, eventually leading to a stable death. However, pulsars challenge that simplicity. They are evidence of how the incredible gravitational forces and the extreme environments of supernova explosions can create new, exotic states of matter. For instance, neutron stars contain matter in a state not found anywhere else in the universe, which forces scientists to reconsider the models of how stars live and die. Additionally, the exceedingly strong magnetic fields and the rapid rotation of pulsars shed light on fundamental physics. The characteristics of pulsars require us to think about force, energy, and matter in new ways. They often spin hundreds of times per second, and their precision in timing can rival the best atomic clocks. This makes them valuable tools for astrophysics, including tests of theories of gravity and the search for gravitational waves. Some pulsars are even part of binary systems, where their interactions with companion stars create conditions that further enrich our understanding of stellar dynamics and evolution. Pulsars serve as both final remnants of a star's life and as powerful beacons guiding our understanding of the cosmos. They challenge existing models of stellar evolution, pushing the boundaries of our knowledge about how stars end. As we study pulsars, we unlock not just the secrets of stellar life cycles, but also the fundamental nature of space, time, and matter itself, revealing the endless mysteries of our universe. The multiverse theory proposes that our universe is just one of many, perhaps an infinite number, of universes that exist simultaneously. Each of these universes could have different physical laws, constants, and properties. Picture a vast cosmic landscape where every potential reality can unfold, from universes identical to ours to those with entirely distinct ways of existing. This concept stretches our understanding of reality itself, opening up fascinating possibilities about existence and the nature of our universe. Supporters of the multiverse theory point to several key arguments and lines of evidence that lend credence to its existence. One significant piece of evidence comes from the field of cosmic inflation. Shortly after the Big Bang, the universe underwent rapid expansion, which some scientists believe could lead to the creation of bubble-like universes. Each of these bubbles could develop with its own unique characteristics, creating a patchwork of diverse universes within a grander multiverse. Another argument draws from the peculiar properties of our universe, particularly the fine-tuning of physical constants. For example, the strength of gravity, the charge of an electron, and other fundamental forces seem finely balanced to allow the formation of stars, galaxies, and ultimately life. The improbability of such a delicate balance occurring by chance leads some scientists to speculate that numerous universes exist, each with varying constants. In this scenario, we just happen to be in a universe that supports life. Lastly, there are theoretical models in physics, particularly from string theory. These theories allow for extra dimensions beyond the three we inhabit and predict a vast number of potential universes. While the direct evidence for the multiverse remains elusive, the implications of advanced theoretical physics and cosmology provide a rich tapestry of support that continues to intrigue scientists and cosmologists alike. The multiverse, if it exists, invites us to ponder not just what is, but what else might be out there, waiting to be discovered. String theory offers a compelling framework that seeks to unify the four fundamental forces of the universe: gravity, electromagnetism, the weak nuclear force, and the strong nuclear force. At its core, string theory suggests that the basic building blocks of the universe are not point-like particles, such as electrons or quarks, but rather tiny, vibrating strings. These strings can vibrate at different frequencies, and the frequency of vibration determines the type of particle and its properties. This innovative idea is exciting because it holds the promise of integrating gravity, which is described by general relativity, with the other forces governed by quantum mechanics. One of the most intriguing aspects of string theory is its proposal that there are additional dimensions beyond the familiar 3 dimensions of space and one of time. While scientists typically consider the universe to have 4 dimensions, string theory requires 10 or even 11 dimensions for mathematical consistency. These extra dimensions are compactified or curled up, making them imperceptible to our everyday experience. This idea sparks curiosity about the nature of reality and whether there could be entire realms of existence just beyond our observational capabilities. However, string theory isn't without its puzzles and controversies. The myriad possible solutions lead to a landscape of options where countless different universes could exist, each with its own set of physical laws. This raises profound questions about the nature of our universe. If so many universes can exist, what determines our own? Are we just one of many, or is there something uniquely special about the conditions we observe? Moreover, since string theory requires energy scales that are currently unreachable by our technology, direct experimental validation remains elusive. The theory is still in the theoretical domain, sparking heated debates among physicists regarding its scientific status. Nevertheless, string theory significantly impacts our understanding of the universe, inviting us to ponder what unifies the forces that shape our reality, while reminding us how much remains to be discovered. Quantum entanglement, a phenomenon where particles become interconnected regardless of distance, challenges our classical perceptions of reality. When 2 particles are entangled, the state of one instantly influences the state of the other, no matter how far apart they are. This strange connection raises profound questions about the nature of reality itself, suggesting that information can traverse vast distances in ways that do not conform to traditional physics. In the context of our observable universe, quantum entanglement pushes the boundaries of how we think about distances and separateness. It introduces a level of interconnectedness that defies our instinctive understanding of space and time. This suggests that at a fundamental level, reality might be more like a vast web of relationships rather than a collection of isolated particles. Such insights prompt scientists to rethink the fabric of the universe and how everything within it may be interlinked. Moreover, entanglement hints at possibilities beyond our observable universe. If entangled particles can influence one another instantaneously, what does this mean for regions of space that we cannot yet see or detect? Concepts like parallel universes and multiple dimensions gain traction within this framework, suggesting that there may be layers of reality that exist just beyond our perception, interwoven yet hidden from our direct experience. Consequently, quantum entanglement does not merely reshape our understanding of particles and forces. It invites us to explore the very nature of existence. As scientists continue to investigate these puzzling interactions, we may unlock deeper truths about the universe, revealing the intricate dance of reality that we are only beginning to comprehend. The theory of cosmic inflation presents a fascinating solution to one of the most enduring questions in cosmology. How did the universe become the vast and intricate tapestry we see today? Proposed in the early 1980s, inflation suggests that shortly after the Big Bang, the universe underwent an exponential expansion. This means that space itself expanded at an astonishing rate, potentially faster than the speed of light, within the first tiny fraction of a second. This rapid inflation helps to explain the large-scale structure of the cosmos in a few significant ways. Firstly, it points to a mechanism that can stretch small quantum fluctuations in the early universe into sizable regions. These tiny fluctuations became the seeds of galaxies and clusters of galaxies as the universe cooled and matter began to clump together under the influence of gravity. Without inflation, these structures might not have formed as uniformly or as evenly as we observe them today. Moreover, cosmic inflation addresses the uniformity of the cosmic microwave background radiation, the faint afterglow of the Big Bang. While regions of the universe that we observe are now separated by vast distances, inflation indicates that they were once closely packed. This shared early state allowed regions to maintain a uniform temperature before space expanded and carried them apart. As a result, we see a surprising homogeneity across the universe's large-scale structure, a connectedness that is established by inflation's early expansion. The theory of cosmic inflation not only enhances our understanding of the early universe's dynamics, but also provides a robust framework for explaining the large-scale organization of matter in the cosmos. It represents a harmonious blend of quantum physics and cosmology, illustrating how phenomena at the tiniest scales can sculpt the universe we see, a spectacular intersection of the infinitesimal and the immense. The holographic principle is a fascinating idea in theoretical physics, suggesting that our three-dimensional universe could be a kind of projection, akin to a hologram. According to this principle, all the information that makes up our three-dimensional reality might be encoded on a two-dimensional surface. This means that, in a sense, the layers of information at the edge of the universe can represent everything we see and experience in our three-dimensional space. This idea emerges from studies in black hole physics and quantum mechanics. For instance, when matter falls into a black hole, it appears that information is lost, leading to contradictions with quantum theory. However, the holographic principle proposes that all the information swallowed by a black hole is stored on its surface, known as the event horizon. This suggests that the interior of the black hole may not be where the fundamental information lies, but rather that it exists outside, represented in a lower dimensional form. Furthermore, the holographic principle resonates with some interpretations of string theory, which posits that the fundamental constituents of the universe are not point particles, but rather tiny vibrating strings. These strings can only exist in specific dimensional configurations, allowing theories to emerge where our space-time reality is viewed as a projection of information organized on a distant surface. This interplay between dimensions challenges our intuitive sense of space and suggests that the cosmos might be far more interconnected and dynamic than we realize. Ultimately, the holographic principle invites us to rethink the nature of reality itself. If our universe is indeed a projection of information, then our understanding of existence could be changed profoundly. It encourages a sense of curiosity about the universe and reminds us that the fabric of reality may be woven from threads we have yet to explore fully. This captivating perspective continues to unfold, opening doors to new questions about the connection between space, time, and the very nature of existence. The cosmic microwave background radiation, often called the CMB, is a faint glow that permeates the universe. This radiation is a remnant from an era just moments after the Big Bang, roughly 380,000 years into the universe's expansion. At this time, the universe cooled enough for electrons and protons to combine and form neutral hydrogen atoms, allowing light to travel freely for the first time. This released an abundance of microwave radiation that we now detect as the CMB. The patterns observed in the CMB are not random. They are filled with information about the early universe. Tiny fluctuations in temperature within this radiation represent regions of differing densities in the primordial plasma from which the universe evolved. These variations played a crucial role in the formation of cosmic structures like galaxies and clusters of galaxies. By studying the detailed patterns in these fluctuations, scientists gain insights into fundamental questions about the universe's composition, dynamics, and even its eventual fate. One of the most compelling aspects of the CMB is what it reveals about the universe's expansion. The uniformity of the CMB suggests that the universe was once in a hot, dense state, while the slight variations can tell us about the initial conditions that led to its current structure. Notably, these patterns indicate that the universe is composed of various components, including ordinary matter, and dark energy, with dark energy playing a significant role in the universe's accelerated expansion. Moreover, when we analyze these fluctuations through sophisticated instruments like the Wilkinson Microwave Anisotropy Probe and the Planck satellite, we find a treasure trove of information about the universe's age, approximately 13.8 billion years, as well as its flat geometry. The CMB serves as a time capsule, offering us glimpses into the universe's infancy and continuing to inform our understanding of its origin, evolution, and the underlying laws of physics that govern all cosmic phenomena. Cosmic strings are hypothetical one-dimensional defects in the fabric of space-time, predicted to arise in certain theories of physics, particularly those connected to the early universe. Imagine them as incredibly thin, yet immensely dense strands stretching across the cosmos, remnants of events when the universe underwent rapid changes, such as phase transitions similar to those that occur when water freezes. If they exist, cosmic strings would be incredibly massive, packing the mass of an entire galaxy into a narrow line. From a theoretical perspective, cosmic strings could offer profound insights into the structure of the universe. They are thought to be key players in the formation of galaxies, as their immense gravitational pull could attract surrounding matter, influencing how cosmic structures evolve over time. Essentially, they act as gravitational anchors, pulling in gas, dust, and other celestial materials to form stars and galaxies. Moreover, cosmic strings could help scientists understand fundamental aspects of physics, including issues related to dark matter and dark energy. If we could detect these strings, it might allow researchers to test models of the early universe, shedding light on phenomena that remain enigmatic, such as inflation, a rapid expansion of space that occurred just after the Big Bang. Such discoveries would not only enhance our grasp of cosmic evolution, but also refine the theories that describe the underlying laws of nature. Intriguingly, cosmic strings could also produce unique signatures in the cosmos, such as gravitational waves. These ripples in space-time could be detected by current and future observatories, providing a potential observational pathway to explore these fascinating structure-forming elements. The existence of cosmic strings might change our understanding of cosmic history and the intricate tapestry that forms the universe as we see it today. The discovery of dark energy has fundamentally altered our understanding of how the universe expands. Initially, scientists believed that the expansion of the cosmos was slowing down due to the gravitational pull of matter. However, observations made in the late 20th century revealed something astonishing. Not only is the universe expanding, but it is doing so at an accelerating rate. This unexpected acceleration pointed toward the presence of dark energy, a mysterious force making up about 70% of the universe. Dark energy challenges conventional ideas about gravity and the universe's fate. We once thought that the gravitational attraction of galaxies and dark matter would eventually dominate and lead to a slowdown or even a reversal of expansion, possibly culminating in a big crunch. However, with dark energy pushing outward, it seems the universe may keep expanding forever, leading to scenarios like the Big Freeze, where galaxies drift apart and stars burn out over trillions of years. This enigmatic energy does not emit light or interact with matter in any observable way, making it notoriously difficult to study. Scientists infer its existence mainly through its effects on the cosmos. For instance, observing distant supernovae has shown that they are further away than they would be if the universe's expansion were decelerating. This finding not only supports the idea of dark energy, but also invites various theories about its nature, including the possibility that it could be a property of space itself, affecting every corner of the universe. As researchers delve deeper into the mysteries of dark energy, they are also addressing some profound philosophical questions. What does the existence of dark energy mean for our understanding of the cosmos? How might it reshape our theories of physics? These challenges push the boundaries of cosmology, igniting curiosity and wonder about the universe's ultimate destiny. The more we learn, the clearer it becomes that the cosmos holds secrets that continue to surprise and inspire scientists and enthusiasts alike. The Great Attractor is a fascinating cosmic entity that resides in the direction of the constellations Centaurus and Hydra. It is an immense gravitational anomaly that affects the motion of galaxies within a substantial region of space, specifically pulling them toward itself. However, its exact nature is somewhat elusive, primarily because it lies behind the Milky Way's dense disk of stars and gas. This backdrop makes it challenging for astronomers to study directly. Despite this, scientists have gathered enough data to understand its significance in the cosmic landscape. At its core, the Great Attractor is thought to contain a significant concentration of mass, possibly a large cluster of galaxies, dark matter, and intergalactic gas. This concentration generates a gravitational pull that influences not just our Milky Way, but also numerous nearby galaxies. Research indicates that our galaxy, along with about 30 others, is moving toward this gravitational focal point at an impressive speed, estimated at around 200 kilometers per second. This motion is not just a curious phenomenon, it highlights the dynamic and interconnected nature of the universe. Interestingly, the Great Attractor is part of a larger structure known as the Laniakea supercluster, which encompasses many galaxy clusters. The existence of such massive structures reveals the complex web of gravity that governs the movement and distribution of galaxies across the universe. As our galaxy journeys toward the great attractor, it is doing so within a broader context of cosmic expansion and gravitational interactions that shape the universe itself. Additionally, the great attractor poses intriguing questions about dark matter and the unseen forces of the universe. Since most of its mass is likely composed of dark matter, which does not emit light or energy, studying this region can shed light on the mysteries of the cosmos. As scientists continue to explore this enigmatic feature, it reminds us that our universe is an ever-evolving tapestry, woven together by gravitational threads that guide the movement of its countless celestial inhabitants. Quasars, or quasi-stellar objects, are among the most remarkable phenomena in the universe. They are incredibly luminous and energetic regions found at the centers of distant galaxies, powered by supermassive black holes feeding on surrounding gas and dust. When this material falls into the black hole, it heats up and emits vast amounts of radiation, often outshining the entire galaxy in which the quasar resides. This intense brightness allows astronomers to observe quasars that are billions of light years away, providing a glimpse into the early universe. One of the most bizarre properties of quasars is their extraordinary variability. Observations show that even though they are extraordinarily bright, their brightness can change dramatically over time, sometimes within days or even hours. This rapid flickering suggests that their emitting regions are surprisingly small, on the order of just a few light days across. Such characteristics challenge our understanding of astronomical objects and suggest that phenomena at these scales behave in unexpected ways, forcing scientists to reconsider the physical mechanisms driving these cosmic beacons. In terms of galactic evolution, quasars provide invaluable insights into the life cycle of galaxies. They often appear during a specific phase, corresponding to the period of peak star formation in the universe, which occurred when it was about 3 billion years old. As these enormous black holes grow and consume surrounding material, they can significantly influence their host galaxies. The energy and outflows produced can effectively regulate star formation and shape the evolution of the galaxy. This interrelationship between quasars and their host galaxies highlights a symbiotic nature of cosmic growth. Ultimately, quasars challenge our understanding of how galaxies evolve over cosmic time. They represent a crucial transition in the life cycle of galaxies, from young star-forming systems to mature, more static states. The study of quasars opens a window into the conditions of the early universe and offers clues about the complex dynamics that drive the universe's evolution, making them essential to our understanding of cosmic history. Anomalous galaxies, often seen as cosmic enigmas, differ significantly from the more familiar galaxy types like spirals or ellipticals. One primary characteristic of these galaxies is their unexpected shapes or structures. While most galaxies tend to exhibit a structured form, such as the classic spiral arms of a Milky Way, anomalous galaxies can appear distorted, irregular, or even fragmented. This irregularity usually results from gravitational interactions, mergers, or collisions with other galaxies, leading to unique evolutionary paths. Another fascinating aspect of anomalous galaxies concerns their stellar populations. Many of these galaxies boast unusually high rates of star formation, but in a chaotic manner. This is in stark contrast to typical galaxies, where star formation occurs in a more orderly fashion, often in defined regions or spirals. The irregular nature of anomalous galaxies can lead to patches of intense activity, resulting in stars being born rapidly and sometimes in groups, which contributes to an uneven distribution of brightness and stellar age throughout the galaxy. Moreover, anomalous galaxies can exhibit unusual chemical compositions. Their star-forming processes can lead to a higher or lower prevalence of certain elements compared to the typical galactic makeup. This might indicate past interactions with other galaxies or intergalactic matter that have enriched or stripped their chemical composition over time. Such variations provide key insights into the history and evolution of these galaxies, revealing their unique journeys through the cosmos. In some cases, scientists have classified specific types of anomalous galaxies, such as dwarf or irregular galaxies, which do not fit neatly into the established categories. Observations of these galaxies challenge our understanding of how galaxies form and evolve, inviting researchers to explore the complexities of cosmic evolution. As we continue to study these fascinating celestial bodies, we unravel new mysteries about the universe's diversity and the processes that shape the cosmos. When galaxies collide, it's not merely a cosmic clash of titans. It's a fascinating encounter that reshapes our understanding of gravitational interactions in the universe. These colossal events are not just about the destruction of stars or the merging of massive structures. They provide key insights into how gravity acts on an enormous scale. Through their interactions, we learn about the dynamics of mass and the intricate dance of stars as they navigate through this gravitational influence. As galaxies approach one another, their gravitational forces begin to tug at each other, causing distortion in their shapes. This gravitational pull can trigger waves of star formation as gas and dust from the galaxies compress and ignite new stars. The result is often a spectacular burst of activity that can create new galactic structures. We see this in examples like the antennae galaxies, where two galaxies collide and form a brilliant spectacle of starburst activity driven by gravitational forces. Moreover, these collisions challenge our understanding of dark matter, an unseen substance that makes up a significant portion of the universe's mass. When galaxies merge, the gravitational interactions also extend to dark matter, revealing how it affects the structure and behavior of galaxies. Observations from such cosmic events have forced scientists to reconsider the role of dark matter in galaxy formation and evolution. As we gather more data from such colliding galaxies, our models of the universe become richer and more complex. Finally, these galactic collisions serve as natural laboratories for testing theories of gravity. They allow astronomers to observe how gravity works in extreme conditions that cannot be replicated on Earth. By studying these phenomena, from the merging of galaxy clusters to the swirling of stars, we deepen our understanding of the fundamental forces that shape the universe around us. So, each galactic collision not only tells us about the involved galaxies, but also reveals universal truths about gravity and the dynamic processes that govern the cosmos. In the grand tapestry of our universe, galaxies are like luminous islands in the vast cosmic ocean, sprawling with stars, dust, and gas. Yet when astronomers observe these galaxies, they encounter a perplexing phenomenon. A significant portion of their mass appears to be missing. This missing mass is primarily believed to be in the form of dark matter, an invisible substance that does not emit, absorb, or reflect light, making it incredibly challenging to detect directly. The implications of this missing mass are profound. According to the laws of physics, the visible matter in a galaxy, including stars and gas, should not be enough to account for the observed gravitational effects, particularly the rotation speeds of galaxies. When scientists measure how quickly different parts of a galaxy are orbiting its center, they find that the outer regions are moving much faster than what one would expect based purely on the visible mass. This discrepancy hints at the presence of an unseen gravitational influence, leading to the conclusion that dark matter makes up a substantial portion of a galaxy's total mass. Dark matter plays a crucial role in the dynamics of galaxies and their formation. It is thought to be distributed in a halo around galaxies, shaping the structure of these celestial bodies. Because dark matter does not interact with electromagnetic forces, it fails to produce any light or other detectable radiation, leaving astronomers to infer its existence through its gravitational effects. This situation complicates our understanding because it suggests that the universe is not just made up of the matter we can observe, challenging our traditional views of mass and energy. As we delve deeper into the mysteries of dark matter, we also grapple with questions about its nature. What is dark matter composed of? Is it made up of exotic particles yet to be discovered? While our knowledge is still evolving, the existence of this elusive mass fundamentally alters our understanding of the universe, pushing the boundaries of science as we strive to unravel the complexities of galaxies and the cosmic landscape. Galactic cannibalism is a fascinating phenomenon in the universe, where larger galaxies pull in and absorb smaller galaxies. This process occurs due to the immense gravitational forces at play in the vast cosmos. When a smaller galaxy ventures too close to a more massive one, the gravitational pull can be so strong that it disrupts and ultimately consumes it. This can lead to some rather spectacular cosmic scenes, as stars and gas from the smaller galaxy are stripped away and incorporated into the larger galaxy. The effects of galactic cannibalism are significant, influencing the evolution and formation of galaxies throughout the universe. In many cases, it can trigger bursts of star formation in the larger galaxy. This happens because when the smaller galaxy is disrupted, it can trigger the gas clouds within it to collapse under their own gravity, leading to the birth of new stars. So, while one galaxy is being devoured, another is being rejuvenated and revitalized. These interactions also play a critical role in the overall structure of our universe. Through this process, galaxies grow larger and more complex. Over billions of years, many of the grand spiral galaxies we observe today have likely undergone numerous mergers and cannibalistic events, which have shaped their current forms. In fact, astronomers believe that the Milky Way, our home galaxy, has a history filled with such encounters, having gobbled up several smaller galaxies during its lifetime. As we look deeper into our universe, we find evidence of these galactic cannibalism events in the form of tidal tails and streams of stars left behind from these smaller galaxies. These remnants allow astronomers to trace the histories of galaxies and understand how they have evolved over time. The intricate dance of formation and absorption continues to be a vital aspect of cosmic evolution, highlighting the interconnectedness of galaxies in the vast expanses of space. Ultra-diffuse galaxies, or UDGs, are fascinating celestial objects that challenge our understanding of how galaxies form and evolve. These galaxies are notable for their large size, yet they contain very few stars, making them appear almost ghostly. This unique characteristic poses a puzzle for astronomers and astrophysicists, primarily because they deviate from the traditional notion that galaxies should be densely populated with stars and gas. Traditionally, models of galaxy formation have suggested that galaxies grow through the accumulation of gas and dust, supplemented by mergers with smaller galaxies. This process typically results in structures that are rich in stars. However, the existence of UDGs, which can contain as little as 1% of the stellar mass of a typical galaxy of similar size, raises questions about how they can maintain a coherent shape and large size without the expected amount of stellar content. Some researchers propose that these galaxies might have formed in low-density environments, where interactions with other galaxies are less frequent. Alternatively, it has been suggested that UDGs may have gone through an evolutionary process that stripped away their stars through various mechanisms, such as gravitational interactions or tidal forces. These scenarios illustrate that galaxy formation is more nuanced than previously thought, and that there are more pathways for galaxy evolution than traditional models account for. UDGs invite us to reevaluate the complexities of the universe. They remind us that there is still much to learn about cosmic structures and their histories. As we explore these enigmatic galaxies further, we gain deeper insights into the nature of dark matter, galaxy morphology, and the very fabric of the universe. The study of ultra-diffuse galaxies is not just about understanding a peculiar group of celestial bodies. It challenges us to rethink the fundamental principles of how galaxies are born and grow across the vast cosmos. Exoplanet K2-141b stands out as an extreme case in the vast cosmos of planetary environments due to its unique conditions that challenge our understanding of what a planet can be. Discovered through the Kepler space mission, K2-141b is classified as a hot Neptune, yet it exhibits characteristics that place it in a category all its own. This mesmerizing planet orbits its star in a mere handful of hours, leading to temperatures that can reach a staggering 3,000 degrees Fahrenheit. Such intense heat makes it one of the hottest known exoplanets. What sets K2-141b apart is not just its brutal temperature. It also has a strikingly different surface compared to what we know from our own solar system. Imagine a landscape dominated by rivers of molten rock. This transformation occurs because any solid surface materials at such high temperatures melt away, creating a seething sea of lava. Scientists speculate that this extreme environment generates extraordinary atmospheric phenomena, possibly including intense storms and turbulent winds. Moreover, K2-141b's proximity to its star results in a peculiar day-night cycle. The same side of the planet consistently faces its star, while the opposite side exists in perpetual darkness. This stark contrast leads to significant temperature differences across its surface, where one side is engulfed in flames and the other may be frigid and unyielding. The extremes of this planet not only paint a picture of a hostile environment, but also provide a fascinating contrast to the more stable, temperate conditions we often see on Earth-like planets. In studying K2-141b, astronomers gain invaluable insights into the diversity of planetary atmospheres and surface conditions. Its existence pushes the boundaries of how we define habitability and encourages scientists to rethink what forms life may take in the universe. By exploring such celestial oddities, we deepen our understanding of the potential for diverse planetary environments far beyond our imagination. The gas giants in our solar system, Jupiter, Saturn, Uranus, and Neptune, present intriguing anomalies that challenge our understanding of planetary formation and evolution. Unlike terrestrial planets, which are primarily rocky and small, these massive worlds are predominantly composed of hydrogen and helium, surrounded by thick, swirling atmospheres. Their immense sizes and rapid rotation lead to intricate weather patterns, exhibiting phenomena that scientists are still working to fully understand. One significant anomaly is Jupiter's Great Red Spot, a colossal storm that has been raging for centuries, if not longer. This storm is so large that it could easily engulf Earth, yet its persistence poses questions about the dynamics of its atmosphere. Researchers are fascinated by how such a storm can last so long and withstand the immense energy of the planet. The Great Red Spot defies some expected behaviors of storms observed on smaller planets, revealing that atmospheric physics operates differently under extreme conditions. Another puzzling aspect of gas giants is the presence of unexpected chemicals and temperatures in their atmospheres. For instance, on Uranus and Neptune, scientists have detected the presence of methane, which gives these planets their striking blue color. Yet, the atmospheric temperatures and pressures there lead to questions about how these molecules behave under such extreme conditions. This raises the possibility that different chemical processes may occur in these distant worlds, leading to atmospheric conditions we are just beginning to comprehend. Lastly, the formation of these gas giants challenges traditional models. Although we have theories about how they came to be, there are still significant gaps in our understanding. How did these planets gather so much gas? And why did they weather their evolutionary paths so differently? Exploring these anomalies not only provides insights into our solar system, but also informs our search for exoplanets in other systems, enriching our understanding of how diverse planetary atmospheres can be throughout the universe. The TRAPPIST-1 system is a remarkable cluster of 7 Earth-sized planets orbiting a star that is much cooler and dimmer than our Sun. This star, located about 40 light-years away in the constellation Aquarius, is classified as an ultra-cool dwarf. The planets are named TRAPPIST-1b through TRAPPIST-1h, and they are all situated in close proximity to one another, making this system particularly interesting for scientists looking for new worlds. What sets the TRAPPIST-1 planets apart from many other exoplanets is their potential to host liquid water. 3 of these planets lie within the star's habitable zone, which is the region where conditions might be right for water to exist in liquid form. This is essential for life as we know it, and it opens up tantalizing possibilities for astrobiology. The unique arrangement and size of these planets mean they are likely to experience gravitational interactions with each other, potentially leading to what is known as tidal heating. This phenomenon can influence their geological activity and atmosphere over time. In addition to their size and location, the TRAPPIST-1 planets have been shown to possess varying atmospheric compositions. This diversity hints at different evolutionary paths despite their similar sizes. Scientists speculate that some may have thick atmospheres while others may be more barren. Recent studies suggest that the conditions on these planets could be vastly different, making them potential candidates for further study in the hunt for extraterrestrial life. Ultimately, the TRAPPIST-1 system serves as a significant focal point in our exploration of the cosmos. It challenges our understanding of planetary systems and provokes deep questions about the universality of life in the universe. With upcoming missions set to closely observe this intriguing system, we may soon gather more clues about these extraordinary worlds and their potential to harbor life. Europa, one of Jupiter's many moons, has captivated scientists for decades, mostly due to its icy surface and the tantalizing hints of a subsurface ocean lying beneath. This ocean, believed to be in contact with Europa's rocky mantle, is considered one of the most promising locations in our solar system to search for extraterrestrial life. The idea is that the heat generated from tidal forces, as Europa is pulled and stretched by Jupiter's immense gravity, creates a warm environment in this ocean that could harbor conditions suitable for life. Recent studies suggest that this subsurface ocean may contain more than just water. It is possible that it is rich in essential chemical ingredients. The presence of salts, particularly magnesium sulfate, has been detected on Europa's surface, hinting that similar materials could exist in the ocean below. These salts are crucial because they can influence the ocean's chemistry, potentially creating a habitable environment similar to Earth's deep-sea hydrothermal vents, where life thrives in complete darkness, relying on chemical reactions rather than sunlight. Another exciting aspect of Europa is the potential for a nutrient cycle, supported by the interaction between the ocean and the Moon's rocky crust. This could mean that chemical reactions, which are essential for life, are occurring at the seabed, further enriching the subsurface ocean with vital energy sources. In fact, scientists believe that if microbial life exists anywhere beyond Earth, it might thrive in such environments where geothermal energy and chemical nutrients are available. Exploration missions like NASA's upcoming Europa Clipper aim to delve deeper into these mysteries. By analyzing the ice cover, measuring the thickness of the ocean, and using powerful instruments to search for biosignatures, we may soon find clues that bring us closer to answering one of humanity's profound questions. Are we alone in the universe? The discoveries about Europa's subsurface ocean continue to inspire and maintain our curiosity about the potential for life beyond our home planet. The surface of Mars tells a captivating story of our neighboring planet's past. Over billions of years, astrogeological processes like volcanic activity, erosion, and sedimentation have shaped its landscape. Scientists study these processes to piece together evidence surrounding the possibility of ancient life on Mars. Among the most compelling features are vast flood channels, ancient riverbeds, and the polar ice caps, which all suggest that liquid water once flowed freely across the Martian surface. Volcanic activity played a significant role in this transformation. Massive volcanoes like Olympus Mons highlight a time when Mars was geologically active. This activity would have released gases into the atmosphere, potentially warming the surface and creating conditions suitable for liquid water. The existence of water is crucial because it is one of the key ingredients for life as we know it. As researchers analyze rock formations and sediment deposits, they find minerals like clays and sulfates that typically form in wet environments, reinforcing the idea that Mars once had a more hospitable climate. Erosion processes, driven by wind and possibly ancient flowing water, sculpted the Martian landscape, creating valleys and canyons. These features provide clues about how long water might have existed on the surface. Some scientists argue that if water was present for extended periods, it could have created diverse environments where life might have once thrived. However, the debate continues, as the harsh conditions we see today could have evolved over millions of years, leading to the current cold, arid landscape that seems inhospitable. The geological evidence gathered from Mars generates discussions about the planet's ability to support life in the past. The interplay of volcanic activity, erosion, and the history of water on Mars continues to engage scientists and enthusiasts alike, inviting us to ponder the ancient habitability of our red neighbor. As we uncover more about these processes, we may soon find ourselves closer to answering the age-old question: did life ever exist on Mars? Abnormal cosmic rays, those particles that come from beyond our solar system and travel at speeds close to the speed of light, have significantly shaped our understanding of high-energy astrophysics. These rays primarily consist of protons and atomic nuclei, and their study allows scientists to probe the most extreme and energetic events in the universe. For decades, researchers have been intrigued by their origins and the mechanisms that accelerate them to such tremendous energies. One of the most compelling aspects of these rays is their connection to massive cosmic phenomena, such as supernovae and active galactic nuclei. When cosmic rays enter Earth's atmosphere, they collide with air molecules, resulting in cascades of secondary particles. Scientists analyze these interactions to gain insights into the conditions and environments under which these high-energy particles are produced. Observations indicate that many of the highest energy cosmic rays likely originate from regions near black holes or neutron stars, where the gravitational forces are so intense that they can accelerate particles to extreme speeds. Additionally, the abnormal cosmic rays have posed challenges and sparked new questions within the field. For instance, some cosmic rays have been detected with energy levels that seem impossible to achieve under known cosmic conditions, suggesting that there might be processes or sources still undiscovered. This has led to a surge in research aimed at understanding these exceptional events, pushing the boundaries of what we know about the universe and prompting the development of more advanced observational techniques and technologies. Abnormal cosmic rays serve as cosmic messengers, revealing secrets about the most violent and energetic processes occurring in the universe. Their study not only enhances our comprehension of high-energy astrophysics, but also fuels our curiosity about the underlying mechanisms and origins of these enigmatic phenomena. With every new discovery, we are reminded of how much there is yet to learn about the vast cosmos that surrounds us. In August 1977, a radio telescope in Ohio recorded a strong narrowband radio signal that sparked excitement across the scientific community. This signal, later termed the WOW signal, lasted for 72 seconds and appeared to come from the direction of the constellation Sagittarius. When astronomer Jerry R. Amon first spotted the unusual signal while reviewing data, he was so astonished that he circled it in red ink and wrote "WOW" in the margins, giving the phenomenon its enduring name. The excitement around the WOW signal lies in its unexplained nature. It possessed characteristics that distinguished it from regular cosmic noise or earthly interference. While typically radio waves from space are either too weak or too broad, this signal had a distinct quality, suggesting a possible artificial origin. Theories ranged from it being a natural celestial phenomenon to a transmission from an extraterrestrial civilization, adding a layer of intrigue and speculation to its existence. However, despite extensive searches, the WOW signal has never been detected again. This absence raises numerous questions. What could have caused such an isolated event? Was it a one-off signal from a distant source, or perhaps an unrecognized natural phenomenon that scientists have yet to understand? The lack of repeatability challenges researchers as they strive to determine if the signal was a unique occurrence or indicative of something larger, like alien broadcasts or undiscovered astrophysical processes. Furthermore, the WOW signal does not provide any definitive information that could help identify its origins. The exact frequency it occupied falls within a region that overlaps both natural astrophysical sources and possible extraterrestrial communication attempts. This ambiguity leaves us with not only the mystery of the signal itself, but also wider questions about the universe. Are we alone in this vast cosmos, or is the WOW signal an incomplete message in an ongoing conversation that remains hidden from our understanding? The Voyager spacecraft, launched in the 1970s, have traveled far beyond our solar system, offering invaluable insights into the outer reaches of space. Interestingly, as they journeyed, scientists noticed something puzzling. Both Voyager 1 and Voyager 2 exhibited an unexpected acceleration towards the Sun. This phenomenon, sometimes referred to as the Voyager anomaly, has sparked intriguing questions about our understanding of gravity and the forces at work in space. At first glance, one might assume this acceleration is simply an extension of gravitational pull from the Sun, but the magnitude of this acceleration seems to differ from what classical physics would predict. This discrepancy has led to speculation about various possible explanations, ranging from the influence of unseen matter in the universe to variations in the force of gravity at such vast distances. Understanding this could reshape our fundamental grasp of cosmology and the forces that govern celestial bodies. Researchers have also contemplated whether the spacecraft's propulsion systems could be a factor. Voyager relies on radioisotope thermoelectric generators for power, which provide heat but should not impart significant thrust. Still, some theorists suggest that the residual heat could create minute forces affecting the spacecraft's trajectory. This idea challenges our assumptions about propulsion in the vacuum of space, leading to a deeper exploration of the impact of energy and motion in the cosmos. As scientists continue to analyze data from Voyager, they're not only unraveling the mysteries of the spacecraft's peculiar acceleration, but also challenging established laws of physics. The anomaly invites us to reconsider what we know about gravity, propulsion, and the fundamental workings of the universe. As Voyager sends back more information, we may find that this small anomaly leads to larger revelations about the nature of space-time itself. The Fermi Gamma-ray Space Telescope has provided groundbreaking insights into the universe since its launch in 2008. One of the most intriguing aspects of its findings is the observation of unexplained gamma-ray emissions. These emissions appear to come from various regions of the sky, yet their origins defy our current understanding of cosmic phenomena. For instance, the telescope has detected gamma-ray signals from the center of our Milky Way galaxy that seem to be produced by something other than the expected sources, such as supernova remnants or pulsars. One notable observation involves what scientists have termed the Fermi bubble. These are large, balloon-like structures of gamma-ray emission that extend above and below the plane of the Milky Way. While some scientists speculate that these bubbles are the result of energetic events associated with the supermassive black hole at the galaxy's center, the exact cause remains elusive. This has sparked debates about the nature of the processes that could create such immense and structured emissions. Another puzzling phenomenon is the detection of excess gamma rays from certain regions of the sky that cannot be accounted for by known astrophysical sources. Some researchers have proposed that these observations could hint at the presence of dark matter, yet the evidence remains indirect. If this hypothesis is accurate, it could imply that dark matter particles annihilate or decay in ways that produce gamma rays, presenting a connection between unexplained cosmic observations and fundamental questions about the makeup of the universe. These unexplained emissions challenge established theories and inspire scientists to re-evaluate what we understand about cosmic phenomena. With each new observation, we are drawn deeper into the mysteries of the universe, where the familiar laws of physics interact with the unknown. The ongoing exploration of these gamma-ray anomalies offers a tantalizing glimpse into the uncharted realms of astrological science, encouraging a deeper quest for knowledge in the vastness of space. The Galactic Center, home to the supermassive black hole known as Sagittarius A star, poses intriguing questions for scientists. This black hole, with a mass equivalent to about 4 million suns, is surprisingly low in brightness and activity compared to what many astrophysical models predict. This discrepancy has led researchers to ponder whether our understanding of black holes and the processes surrounding them is complete. Current models generally suggest that supermassive black holes should have vibrant accretion disks, feeding on surrounding gas and dust, which would create bright emissions detectable across vast distances. However, Sagittarius A star appears rather mute, emitting only faint signals. This quietness raises fascinating questions about the black hole's environment. Is it truly consuming very little matter, or is there something unique about how it's interacting with its surroundings? Moreover, studies reveal that the area around Sagittarius A star is not only active, but also complex, filled with intricate stellar dynamics. Dense clusters of stars orbit the black hole, and their gravitational interactions offer clues to the massive entity's influence on the galaxy as a whole. Researchers are now investigating how these stellar movements might stabilize or inhibit the flow of matter toward the black hole, something that could reshape our models of galactic evolution. The enigma of Sagittarius A star is pushing astrophysicists to refine their theories. Each new observation not only deepens our insight into this peculiar giant, but also broadens our understanding of how black holes fit into the larger cosmic puzzle. As we gather more data, we inch closer to a clearer picture, potentially rewriting the rules regarding the role of supermassive black holes in shaping galaxies like our own. The IceCube Neutrino Observatory, situated deep in the Antarctic ice, has provided scientists with groundbreaking insights into high-energy neutrinos coming from cosmic sources. Recently, reports of neutrino anomalies have stirred up excitement in the scientific community. These anomalies suggest that there may be more to our understanding of the universe than previously thought. Essentially, these findings could indicate the presence of new astrophysical phenomena or even hint at the existence of unknown particles. One significant implication of these reports is that they may challenge existing models of particle physics. Generally, neutrinos are thought to have a very tiny mass and interact very weakly with matter. However, the unexpected behavior observed in some neutrino events from IceCube raises questions about the processes that generate these particles. This could potentially mean that we need to revise our understanding of the forces and events occurring beyond our planet, particularly those involving supernovae, neutron star collisions, or even more mysterious astrophysical sources. Furthermore, these anomalies may hold the key to connecting different realms of physics, including cosmic rays and dark matter. Some scientists speculate that the neutrinos detected could originate from dark matter interactions or decay, pointing towards physics beyond the standard model. This could inspire new experiments or observations aimed at uncovering the nature of dark matter, which is believed to make up a significant portion of the universe yet remains elusive and unobserved directly. Ultimately, the implications of neutrino anomalies from IceCube extend beyond mere curiosity. They represent a frontier of exploration that could reshape our understanding of fundamental physics and the universe itself. As researchers dig deeper into these findings, we may be on the brink of discovering new aspects of reality that challenge our established perceptions and lead to a greater comprehension of the cosmos. Time dilation is a fascinating consequence of Albert Einstein's theory of relativity that fundamentally challenges our conventional understanding of time, especially in the context of space travel and high speeds. In everyday life, we perceive time as a constant progression, where one moment flows predictably into the next. However, when we navigate at speeds approaching that of light, or in the presence of strong gravitational fields, this linear perception of time begins to unravel. According to the theory, as an object's speed increases, time for that object slows down relative to a stationary observer. This means that astronauts traveling at great speeds in a spacecraft would age more slowly compared to people remaining on Earth. Imagine a scenario where a twin embarks on a journey through space at near light speed, while the other stays on our planet. Upon returning, the spacefaring twin would find themselves significantly younger than their Earth-bound sibling, a phenomenon often referred to as the twin paradox. Moreover, gravity plays a similar role in time dilation. When you are closer to a massive object, like a black hole or a planet, time passes more slowly for you compared to someone further away. This means that if one could orbit a black hole for a short time, they might return to find that while only a few hours have passed for them, many years have gone by for those farther away from the immense gravitational pull. This intertwining of gravity and time further complicates our traditional beliefs about how time operates universally. Time dilation reshapes our understanding by suggesting that time is not a universal constant. Instead, it becomes a malleable concept that stretches and contracts depending on speed and gravity. This opens up a profound dialogue about the nature of reality itself, prompting questions about how we gauge time and its effects on life as we know it in the cosmos. As our explorations push the limits of space travel, grappling with the implications of time dilation becomes increasingly significant, urging us to rethink what it truly means to experience time. The very concept of wormholes, hypothetical tunnels that could connect distant regions of the universe, opens up a realm of fascinating possibilities. If such structures exist, they might provide shortcuts through space-time, allowing travelers to bridge vast distances in mere moments. Imagine being able to journey from one galaxy to another instantly, bypassing the immense stretches of space that normally take millions of years to traverse. This idea challenges our understanding of travel and could redefine our place in the universe. Furthermore, wormholes could potentially allow for connections not just through space, but also through time. Some speculations suggest that they might enable travel to the past or future, fueling intriguing discussions about causality and the nature of time itself. If one could enter a wormhole at a specific time and emerge in another, it raises questions. Would history change? Could you meet your future self? These inquiries tap into deeply philosophical themes about fate, free will, and the continuity of events. However, the existence of wormholes also introduces paradoxes and challenges. For instance, if it were possible to travel back in time through a wormhole, it could lead to situations like the grandfather paradox, where a time traveler inadvertently prevents their own existence. The implications of such scenarios boggles the mind and lead scientists to investigate whether physical laws might ultimately prevent such travel from being feasible or safe. Despite these speculations remaining largely theoretical, Discussions about wormholes encourage innovative thinking about the universe's structure. They prompt scientists to explore exotic forms of matter and energy that might be needed to create and stabilize a wormhole, further expanding the boundaries of cosmological understanding. Whether or not they exist, the mere idea of wormholes inspires wonder and a sense of limitless possibilities in the vast cosmos we inhabit. As we delve into the mysteries surrounding black holes, one of the most perplexing aspects is the phenomenon of temporal anomalies. These anomalies often arise from the extreme gravitational forces present near black holes, which significantly distort time. This distortion leads to situations where time behaves in unexpected ways, creating a challenge to our traditional understanding of causality, the principle that cause precedes effect. To comprehend this better, let's consider the concept of time dilation. Near a black hole, the intense gravity warps both space and time. An observer far from the black hole, watching an object fall into it, might perceive the object's descent as slowing down, never quite seeing it cross the event horizon, the boundary beyond which nothing can escape. Meanwhile, for the object itself, time keeps flowing normally until it reaches the singularity. This discrepancy raises profound questions. If different observers experience time so differently, can we really trust a linear sequence of events? Moreover, these temporal anomalies suggest intriguing scenarios, such as the possibility of information loss when something is swallowed by a black hole. If the traditional chain of cause and effect breaks down, could this mean that events occurring near black holes might not adhere to the same temporal rules we experience outside of them? These uncertainties challenge the foundational aspects of physics and drive researchers to rethink the fundamental nature of reality. Ultimately, exploring these temporal anomalies invites us to reconsider our concepts of time, causality, and the universe itself. It opens a rich dialogue within the scientific community about how we understand the interactions of forces at play, pushing the boundaries of our knowledge further than ever before. In contemplating the mysteries of black holes, we are not just seeking answers about the cosmos, but also deep philosophical insights into the very nature of existence and the fabric of time itself. The behavior of atoms in extreme gravitational fields, especially those near black holes, presents an intriguing puzzle to scientists. In regions with intense gravity, such as the vicinity of a black hole, the very fabric of space-time is warped. This distortion affects how matter and energy behave. Atoms, the tiny building blocks of matter, experience profound changes in their interactions and properties under such conditions. One of the most captivating aspects of this environment is the phenomenon known as gravitational time dilation. This concept suggests that time moves differently in strong gravitational fields compared to weaker ones. For observers far away from a black hole, it would appear as if time has slowed down for objects falling into the black hole. Atoms, influenced by these extreme conditions, could behave unpredictably. Their energy levels might shift dramatically, impacting chemical reactions and the stability of matter itself. Moreover, the immense gravitational pull can lead to effects like spaghettification, where objects are stretched and compressed as they approach the black hole. This intense tidal force can disrupt atomic structures, leading to fascinating behaviors that challenge our understanding of chemistry and physics. This raises essential questions. How do bonds between atoms hold up under such strain? Can new states of matter emerge in these extreme environments? As we continue to explore the universe and learn more through advanced telescopes and theoretical models, our understanding of atoms under extreme gravity will evolve. Each discovery brings us closer to unraveling the mysteries of the cosmos, revealing not only the strange behavior of atoms near black holes, but also the deeper laws that govern our universe as a whole. The elegance of these phenomena invites us to ponder the nature of reality itself and our place within it. The cosmic web is a fundamental aspect of our universe's composition and structure. Imagine a vast, intricate network stretching across the cosmos, composed of filaments of dark matter and gas. These filaments set the stage for galaxies and galaxy clusters to form, gathering matter along their lengths in a beautiful ballet of attraction, influenced by gravity. Along these strands, we find vast voids where little matter exists, creating a stark contrast that emphasizes the intricate arrangement of the universe. One of the most fascinating roles of the cosmic web is how it influences the distribution of galaxies. Within this web, galaxies are not randomly scattered, but are aligned along these filaments. As gases flow along these structures, they condense to create stars and galaxies, forming a rich tapestry of light and dark that scientists are only beginning to understand. This interplay of matter leads to the breathtaking formation of clusters, which can contain thousands of galaxies, tied together by gravitational forces shaped by the web itself. However, the cosmic web isn't just a static structure, it holds mysteries that intrigue astronomers and physicists alike. For instance, about 85% of the universe's matter is thought to be dark matter, which cannot be seen directly. Its influence is felt in the way galaxies move, but its true nature remains elusive. Questions about how dark matter interacts with regular matter within the cosmic web continue to puzzle scientists as they seek to unlock the secrets of these invisible threads. Moreover, the precise configurations of the cosmic web are still not fully understood. The distribution of galaxies and the formation of voids are influenced by a mix of cosmological forces, yet the underlying physics driving these processes is complex and sometimes contradictory. Continuing studies, including advanced simulations and observational campaigns, hope to clarify these mysteries, reminding us that the universe is a dynamic and ever-evolving entity, still revealing its wonders to us. The concept of dark flow presents a fascinating conundrum for cosmologists trying to unravel the complexities of the universe's structure. Essentially, dark flow refers to the observed motion of galaxy clusters that seem to move in a preferred direction, deviating from what we understand about the cosmic microwave background radiation. This radiation is essentially the afterglow of the Big Bang and acts as a backdrop for the movement of everything in the universe. The surprising part is that this flow does not align with the cosmic expansion predicted by our current models. As researchers dive deeper, the implications of dark flow become even more intriguing. Observations have suggested that these clusters are carrying a significant amount of mass with them. This raises the question, what could be exerting this influence? One possibility is that these movements point toward the existence of structures beyond the observable universe, possibly large superclusters or even other cosmic entities that we have yet to detect. This notion challenges the very limits of our understanding about what lies beyond the reaches of our observational capabilities. Cosmologists have been grappling with these phenomena as they attempt to reconcile the unexpected movements with existing theories. This provides an exciting opportunity to rethink our models of cosmic evolution and the large-scale structure of the universe. It invites researchers to question the completeness of the current cosmological framework, which relies heavily on principles derived from events that occurred shortly after the Big Bang, and encourages them to explore new hypotheses. Ultimately, dark flow sparks curiosity and inspires deeper inquiry into the cosmos. It serves as a reminder that despite the vast knowledge we have accumulated about the universe, significant mysteries still linger just beyond our understanding. Each new discovery pushes the boundaries of science, prompting further exploration and experimentation, and in doing so, deepening our appreciation of the intricate tapestry of our universe. The cosmic horizon problem is a fascinating puzzle in cosmology concerning the limits of what we can observe in our universe. Imagine the universe expanding from a hot, dense state nearly 14 billion years ago. As it grew and cooled, light and other forms of radiation began to travel across the cosmos. However, because of this expansion, there are regions of the universe that we can never observe directly, even with our most powerful telescopes. This raises the question, why are the temperature and density of the cosmic microwave background radiation so uniform, even across areas that seem too distant to have ever exchanged information? One leading theory to address this puzzle is called inflation. This idea suggests that moments after the Big Bang, a rapid expansion occurred, causing the universe to grow exponentially in a minuscule fraction of a second. During this period, regions that are now far apart were once much closer together, allowing them to share the same physical conditions and become uniform in temperature. When inflation slowed down, these regions drifted apart, but they retained a similar signature, which we see today as the uniform cosmic background radiation. Another perspective comes from the concept of quantum mechanics. According to some theorists, fluctuations in a quantum field could have influenced the early universe's structure. This means that tiny variations occurring at an almost subatomic level might have seeded the universe with the slight differences we observe today. These fluctuations would be smoothed out across vast stretches of space, which could also explain the uniformity of the cosmic microwave background. The edge of our universe, as emerging from these theories, does not entail a physical boundary, but rather limits imposed by the speed of light and cosmic expansion. We can never observe anything beyond that cosmic horizon. So the cosmic horizon problem reveals a central aspect of our universe. Its vastness is not just spatial, but also temporal, as we grapple with the implications of what lies beyond our current observational limits. This leads to deeper questions about the nature of reality itself, inviting us to explore further with our scientific instruments and imaginations. Type Ia supernovae are remarkable celestial events that offer valuable clues about the universe's expansion and cosmic acceleration. These supernovae occur when a white dwarf star accumulates enough material from a companion star, typically a red giant, until it reaches a critical mass. This accumulation causes a runaway nuclear fusion reaction, leading to a cataclysmic explosion. The consistency in their brightness makes them excellent standard candles for astronomical measurements. When astronomers observe Type Ia supernovae, they compare their intrinsic brightness to how bright they appear from Earth. Because these supernovae have a similar peak brightness, scientists can calculate their distance with the utmost precision. By mapping these distances against their redshifts, which indicate how much the universe has expanded since the explosion, researchers can infer how fast the universe is expanding. Interestingly, data from these supernovae revealed an unexpected discovery in the late 1990s. Instead of gradually slowing down due to gravity, the rate of expansion is increasing. This surprising finding suggested that something later termed dark energy is pushing galaxies apart. Type Ia supernovae effectively became cosmic beacons, illuminating this mysterious force dominating the universe's fate. By studying these supernovae, scientists have not only traced the expansion history of the universe, but have also delved deeper into the underlying physics of dark energy. The uniformity and reliability of Type Ia supernovae allow astronomers to understand better how this enigmatic energy influences cosmic evolution, prompting further exploration into the very fabric of our universe. The formation of the first stars in the universe, often referred to as population 3 stars, remains shrouded in mystery and presents several unresolved scientific questions. These stars formed during a time known as the Cosmic Dawn, more than 13 billion years ago, when the universe had cooled enough for hydrogen and helium gas to coalesce into the first stellar bodies. However, the precise mechanisms that initiated their formation are still a subject of intense research. One key issue is understanding the cooling processes of primordial gas. Without the metals created in later stellar generations, the gas clouds were primarily composed of hydrogen and helium. As such, the methods through which these gases lost heat to collapse under their own gravity are not fully understood. Current theories suggest that molecular hydrogen may have played a critical role, but the details of this process remain elusive. How efficiently this gas could cool enough to initiate star formation is still up for debate among cosmologists. Additionally, there's ongoing discussion about the mass range of these early stars. Theories propose that population 3 stars were massive, perhaps much larger than stars we see today, which could have implications for their life cycles. The uncertainty surrounding their masses complicates our understanding of their evolutionary paths and the end-of-life supernova processes. These massive stars, when they eventually exploded, seeded the universe with heavier elements, setting the stage for the subsequent generations of stars and galaxies. Lastly, our observational capabilities play a role in this mystery. Despite significant advancements in technology, direct observation of population 3 stars has proven challenging. Most evidence comes from indirect measurements or simulations, which adds another layer of uncertainty about their characteristics. Finding and studying these ancient stars would provide invaluable insights into the early universe. But for now, they remain just beyond our reach, igniting our curiosity as we look to the cosmos for answers. Galaxies are not static entities. They are dynamic systems that often collide and merge with each other across the vast stretches of the universe. When two galaxies come together, the process is a complex ballet of gravitational interactions, swirling gas, and the eventual reshaping of the involved galaxies. During such mergers, the gravitational pull of each galaxy can trigger bursts of star formation as regions of gas and dust get compressed. This can lead to the creation of new stars at a staggering rate, sometimes resulting in thousands of new stars forming in just a short span of time. The merging of galaxies also has remarkable implications for their structure and evolution. When two galaxies collide, they don't simply bounce off each other. Instead, they can end up entangled, leading to new structures such as elliptical galaxies, which often emerge from such interactions. Over time, as the stars in these galaxies continue to interact, a new, larger galactic structure takes shape, often characterized by a more random star movement compared to the organized spirals of the original galaxies. Furthermore, these cosmic mergers can play a significant role in the cosmic web we observe in the universe today. Galaxies clump together, forming clusters, and through these processes, they can redistribute matter, influence dark matter distribution, and even affect the path of intergalactic gas flows. The ancient history of our own Milky Way galaxy includes several mergers with smaller galaxies, which contributed to its current structure and the distribution of stars and stellar remnants we see today. As we gaze into the depths of space using advanced telescopes, we're uncovering evidence of these ancient mergers taking place. The more we learn about this galactic choreography, the more we realize that mergers are not just cosmic accidents. They are fundamental processes that drive the evolution of galaxies, shaping the universe for billions of years and leading to the rich tapestry of structures we observe in the cosmos today. To understand how dark matter influences galaxies, we first need to recognize that it makes up a significant portion of the universe's total mass. Estimates suggest around 85%. Dark matter does not emit or reflect light, making it invisible and challenging to study directly. However, its existence is inferred through its gravitational effects on visible matter, radiation, and even the structure of the universe itself. As galaxies form and evolve, they are surrounded by vast halos of dark matter. These halos exert a gravitational pull on the galaxy, affecting the motion of stars and gas within it. For instance, when scientists observe the rotation curves of galaxies, they notice that outer stars orbit at speeds that do not decrease as expected based on the visible mass alone. Instead, they maintain high speeds thanks to the unseen mass provided by the dark matter halo. This discrepancy gives us crucial evidence of dark matter's dominance in galactic dynamics. Moreover, dark matter plays a key role in the formation and clustering of galaxies. Early in the universe's history, slight fluctuations in density allowed dark matter to clump together, forming gravitational wells. These wells acted like seeds for the formation of galaxies and galaxy clusters. Over billions of years, baryonic matter composed of atoms falls into these clumps, creating the galaxies we observe today. The intricate interplay between dark matter and visible matter shapes the very structure of the universe. Dark matter profoundly influences both the movement and structure of galaxies. It dictates how fast stars move within a galaxy and lays the foundation for galaxy formation by providing the necessary gravitational framework. Although intangible, dark matter's impact is essential for understanding the cosmos, revealing a hidden yet vital component of our universe. Tidal forces play a critical role during galaxy mergers, acting like cosmic puppeteers as they reshape the destinies of these vast collections of stars and gas. When two galaxies approach each other, their gravitational pull creates dramatic interactions. This gravitational influence stretches and distorts them, sometimes leading to the formation of long streams of stars and gas known as tidal tails. These structures offer a fascinating glimpse into the gravitational ballet occurring in our universe during such energetic encounters. As galaxies engage in this cosmic dance, the distribution of stars and gas becomes significantly altered. Regions of high density can form where the gravitational tug is strongest. These dense areas often ignite bursts of star formation, a phenomenon known as starburst activity. Matter, once relatively static, is pushed together, leading to conditions ripe for new stars to be born from the collapsing clouds of gas and dust. This transformation can elevate the star formation rate dramatically, sometimes increasing it by several times. Moreover, while tidal forces are catalyzing new stellar births, they can also disrupt existing star systems. These interactions can fling stars from their homes, scattering them into the intergalactic medium or into other regions of the merging galaxies. This lively exchange can lead to diverse stellar populations, with some areas becoming densely packed with young, hot stars, while others may experience a quieter, more subdued star formation environment. In the aftermath of the merger, the remnants of these galaxies often settle into a more stable configuration, resulting in an elliptical galaxy, which tends to exhibit a lower rate of star formation compared to spiral galaxies. This evolutionary journey highlights the complex relationship between gravitational interactions and the life cycles of stars, revealing how our universe's grand architecture is continually shaped by these wondrous cosmic events. Satellite galaxies are like page markers in the grand story of our Milky Way. They offer valuable insights into the history and evolution of our galaxy, much like chapters in an ongoing narrative. The Milky Way is surrounded by at least 50 known satellite galaxies, the most notable being the Large and Small Magellanic Clouds. Their proximity allows astronomers to study their properties in detail, revealing clues about how galaxies form and grow over time. These satellite galaxies are remnants of the early universe, capturing conditions that existed billions of years ago. As they orbit the Milky Way, they experience gravitational interactions that can shed light on the processes of galaxy formation and evolution. For instance, when a satellite galaxy approaches the Milky Way, it can be distorted and stripped of its stars and gas. Studying these interactions helps scientists understand how larger galaxies consume smaller ones, a process known as galactic cannibalism. Additionally, satellite galaxies host different stellar populations, some of which are among the oldest known stars. By analyzing these ancient stars, astronomers can unravel the timeline of star formation and the chemical evolution of the galaxies involved. The chemical compositions of these stars reveal how many elements were produced in earlier generations of stars and how they impacted the environment around them. This information is crucial for understanding the Milky Way's development through time. Ultimately, the study of satellite galaxies enriches our comprehension of the Milky Way's past and sheds light on the broader universe. By piecing together how these smaller galaxies interact with our own, scientists can better appreciate the complex dynamics that govern galactic evolution. In this sense, satellite galaxies do not just orbit the Milky Way, they are vital narrators in the ongoing epic of our cosmic neighborhood. Galactic redshift is a fascinating phenomenon that occurs when light from distant galaxies shifts toward longer, redder wavelengths as it travels through space. This shift is a direct result of the expansion of the universe. Think of it like the way sound waves stretch out as a train moves away from you. The frequency lowers and the sound gets deeper. In the same way as galaxies move away from us, the light they emit stretches, causing that redshift. The redshift is not just a simple optical effect, it provides profound insights into the universe's structure and dynamics. When astronomers observe light from distant galaxies, the degree of redshift informs them about how fast those galaxies are receding. Edwin Hubble, in the early 20th century, linked the amount of redshift to the distance of galaxies, leading to the groundbreaking realization that the universe is expanding. This means that the more distant a galaxy is, the faster it appears to be moving away. This discovery changed our understanding of the cosmos. It indicated that space itself is expanding, carrying galaxies along with it, rather than galaxies merely moving through a static space. The implications are remarkable. The universe began from a single point in the Big Bang and has been growing ever since. This expansion informs our models of cosmology and helps scientists study the conditions of the universe shortly after its birth. Further investigation into galactic redshift has also led to intriguing questions about the fate of the universe. Depending on the density of matter and energy within the cosmos, theories about its ultimate destiny vary, from continuous expansion to a potential collapse. Understanding redshift, therefore, is not just about what we see today, but about decoding the history and future of the entire universe. The more we learn about this expanding tapestry, the more we appreciate the intricate and dynamic nature of the cosmos we inhabit. The discovery of new celestial bodies has profoundly altered our understanding of the solar system and our place within it. Traditionally, we viewed our solar system as a neatly ordered collection of planets orbiting the Sun. However, As astronomers have identified an increasing number of objects beyond the main planets, that perception has evolved. This shift began in earnest with the discovery of Pluto in the early 20th century and has accelerated with the advent of more powerful telescopes. For instance, the unveiling of dwarf planets like Eris and Haumea has prompted scientists and the public alike to reconsider what constitutes a planet. The revelation that Pluto is not unique in its category has led to a broader, more nuanced definition of these celestial bodies, marrying scientific rigor with our natural human curiosity. This has opened up a rich dialogue about the nature of the solar system and how we classify our cosmic neighbors. Additionally, the ongoing exploration of the Kuiper Belt and the more recently discovered Oort cloud reveals a dynamic and populous frontier far beyond the traditional planets. These regions are populated with thousands, if not millions, of icy bodies and remnants from the solar system's formation. Understanding these areas gives us clues about the early conditions of the solar system and the processes that shape the planets. Moreover, the discovery of exoplanets, worlds beyond our solar system, has inspired a deeper exploration of what lies beyond our immediate neighborhood. These findings raise intriguing questions about the variety of planetary systems in the universe and the potential for life beyond Earth. In this way, as we uncover more celestial bodies, we are continually redefining not just our solar system, but also the broader cosmos, painting a richer and more intricate picture of the universe that surrounds us. The Voyager missions, launched in the late 1970s, have provided humanity with profound insights into our solar system and beyond. As these spacecraft journeyed farther than any human-made objects before them, they unveiled some deep mysteries. One such enigma is the nature of the heliosphere, the vast bubble created by the solar wind that envelops the solar system. When Voyager 1 crossed the boundary into interstellar space in 2012, it sent back data that challenged our understanding of the solar system's edges and the complex interactions between solar winds and cosmic rays. The interaction of the solar wind with interstellar medium revealed variations in particle densities that suggested a dynamic environment at our solar system's frontier. Prior to this, scientists believed the heliosphere was relatively stable, but Voyager's findings showed that it is actually shaped by a combination of solar activity and the more turbulent interstellar medium. This discovery not only piqued scientific interest, but opened new questions about how different regions of space interact, underscoring the need for more exploratory missions to deepen our understanding of these phenomena. Additionally, the two Voyager spacecraft discovered an unexpected phenomenon regarding the magnetic fields of planets. For instance, Voyager 2's flyby of Uranus and Neptune revealed complex magnetic field structures that were not only tilted, but also offset from the planet's centers. This prompted scientists to rethink the formation and evolution of planetary magnetic fields, mysteries that ripple through the broader narrative of planetary science and magnetism in celestial bodies. The significant data obtained from both the Voyager missions have inspired subsequent missions and studies. They have laid the groundwork for a new generation of explorers that will seek to investigate deeper into the cosmos. NASA's plans for missions like the James Webb Space Telescope, which will look back in time to understand the early universe, and the Europa Clipper mission, which hopes to study Jupiter's icy moon for signs of habitability, are directly influenced by the questions and mysteries illuminated by the Voyagers. The legacy of Voyager is not just its discoveries, but its ability to spark curiosity, leading us to explore the cosmos with renewed vigor. The search for extraterrestrial intelligence, often referred to as SETI, introduces numerous complexities to our understanding of life beyond Earth. For starters, when we consider the possibility of intelligent life elsewhere in the universe, we are prompted to redefine what we mean by life. Traditionally, life has been defined by certain biological markers like carbon-based organisms or those that require water. However, the search for extraterrestrial intelligence challenges these notions, pushing scientists to think beyond our Earth-centric perspective. Moreover, the vastness of the universe complicates matters further. The sheer number of stars is staggering, over 100 billion in our galaxy alone, with potentially even more planets orbiting them. Each of these planets presents a unique environment where life could theoretically thrive, yet we have very little idea of how life might evolve in conditions that differ vastly from those on Earth. This uncertainty raises profound questions, such as how we would recognize life forms that don't share our biochemical foundations or types of intelligence. Additionally, there's the matter of communication. If intelligent life does exist, it might not be using technology similar to ours, or it could be communicating through means we do not yet comprehend. This means that even if we hear signals from space, they may not even be intended for us. The understanding of intelligence itself becomes a philosophical dilemma. Can we identify signs of intelligence that are fundamentally different from our own? Finally, this search connects deeply with our understanding of ourselves. If we were to find indicators of extraterrestrial intelligence, it would not only redefine our place in the cosmos, but also ignite questions about our own evolution and purpose. The implications of such a discovery are vast, unraveling previous assumptions about what it means to be intelligent and alive in this ever-expanding universe. Each of these complexities enriches our search, making it as much a journey of self-discovery as it is an exploration of the cosmos. The Hubble Space Telescope has been a revolutionary instrument in our exploration of the universe since its launch in 1990. One of its most profound contributions has been the discovery of the accelerating expansion of the universe. Observations of distant supernovae, exploding stars that shine brighter than entire galaxies, revealed that not only is the universe expanding, but that this expansion is speeding up. This unexpected finding has led astronomers to consider the existence of a mysterious force known as dark energy, which is thought to make up about 70% of the universe. Hubble has also played a crucial role in refining our understanding of galaxies. Through its sharp images, we have been able to observe galaxies forming, merging, and evolving over billions of years. The telescope captured the rich tapestry of galactic structures, from beautiful spirals to elliptical shapes, unveiling the complex histories behind them. These observations have helped scientists piece together the timeline of galaxy formation in the universe, painting a more intricate picture of how galaxies influence each other and contribute to cosmic evolution. Additionally, Hubble's detailed observations have shed light on the life cycles of stars. From their birth in clouds of gas and dust to their explosive deaths as supernovae, the telescope has allowed us to witness these events in real time. Its ability to peer deep into space has made it possible to find young stars forming in remote parts of the universe, which helps us understand the conditions that foster star formation and the role of stars in galactic ecosystems. Moreover, Hubble has forever changed our perspective on the universe beyond our Milky Way. Through its deep field images, we have glimpsed thousands of galaxies in a single patch of sky, revealing a vast and complex cosmic web. This profound view highlighted that we are part of a much larger universe, full of mysteries yet to unravel. Hubble has not just reshaped our scientific understanding, it has rekindled our curiosity about the cosmos, encouraging generations to look up and ponder the nature of our existence among the stars. The James Webb Space Telescope, often referred to as Webb, is set to revolutionize our understanding of the universe. Scheduled for a long-anticipated launch, this powerful observatory will delve deeper into the cosmos than we ever have before. By using a variety of advanced technologies, Webb will be capable of observing celestial objects that are billions of light-years away. This means it can effectively look back into time, providing insights into the early universe, its formation, and the many mysteries that have eluded scientists for generations. One of Webb's most exciting features is its ability to detect infrared light. This is significant because many cosmic phenomena, such as the dust surrounding stars or the remnants of the early universe, emit light in this spectrum. Traditional telescopes like the Hubble primarily observe visible light, which can miss these critical aspects. By capturing infrared frequencies, Webb can identify hidden structures, trace the formation of galaxies, and even study the atmospheres of distant exoplanets, potentially revealing conditions for life beyond Earth. Moreover, Webb is engineered to explore new anomalies by employing a suite of cutting-edge instruments, including a highly sensitive camera and spectrographs. These tools enable astronomers to analyze the chemical compositions of celestial bodies and even measure their light curves, which can indicate unusual behavior. For instance, by studying how starlight dims when a planet passes in front of its host star, we gain valuable information about the planet's size and atmospheric conditions. Such detailed observations could uncover not just known phenomena, but perhaps entirely new classes of objects in our universe. The James Webb Space Telescope promises to significantly enhance our understanding of cosmic anomalies through its ability to detect a wider range of light frequencies and its state-of-the-art observational tools. The data gathered from upcoming missions will likely challenge existing theories and lead to groundbreaking discoveries, potentially reshaping the very foundations of cosmology. With this new era of exploration on the horizon, the scientific community waits with bated breath for the revelations that await us in the depths of space. In recent years, the vast expanse of space has delivered a collection of unusual signals that have sparked intrigue and speculation about the possibility of advanced civilizations beyond our planet. One of the most famous examples is the WOW signal, detected in 1977. It was a strong, narrowband radio signal that lasted for 72 seconds and came from the direction of the constellation Sagittarius. Despite numerous attempts to redetect it, the signal remains a mystery, leading many to wonder if it was a transmission from an intelligent source or simply a natural phenomenon. More recently, astronomers have observed a series of fast radio bursts, or FRBs. These bursts are brief but extraordinarily powerful flashes of radio waves emanating from distant galaxies. While many of the sources are still not fully understood, researchers have pondered whether some of these bursts could be the result of advanced technology, possibly signaling communications from faraway civilizations. The frequency and strength of these signals challenge our understanding of cosmic activity, making them a tantalizing focus of exploration in the search for extraterrestrial intelligence. Another captivating discovery came with the identification of unusual light patterns from distant stars, such as KIC 8272. It was noted that these variances in brightness did not align with typical stellar behavior. Some scientists proposed that these irregularities could be the result of massive structures, sometimes whimsically dubbed megastructures, potentially built by advanced beings to harness energy from their stars. Though more conventional explanations exist, like dust clouds or comets, the connection to possible extraterrestrial engineering adds an exciting layer to our quest for understanding. As we continue to explore the cosmos with ever more sophisticated tools, these peculiar signals and phenomena elevate our quest to understand whether we are truly alone in the universe. Each discovery brings with it the hope of unraveling the mysteries that lie beyond our own world. Scientists remain vigilant, analyzing the data for patterns and anomalies, as the search for signs of intelligent life pushes the boundaries of our understanding further into the vast and enigmatic cosmos. The term Dyson sphere originates from the theoretical ideas of physicist Freeman Dyson, who proposed a way for advanced civilizations to harness the energy of their stars. Instead of simply using the energy from a planet's surface, Dyson imagined a vast structure or collection of structures that could encompass a star, capturing a significant part of its energy output. This idea leads to various interpretations, from a solid shell around a star to more flexible systems made up of satellites orbiting the star. The implication of Dyson spheres is profound when we consider the energy consumption of civilizations. A civilization advanced enough to create such a structure would likely be categorized as a Type II civilization on the Kardashev scale, a method scientists use to measure a civilization's technological advancement based on its energy consumption. While a Type I civilization harnesses all the energy available on its home planet, a Type II would be able to exploit the energy of an entire star. This opens up fascinating possibilities about how we view life in the universe. Interpreting Dyson spheres also raises questions about sustainability and energy efficiency. If a civilization can build such structures, it suggests a level of technology that might lead to significant enhancements in energy management. Rather than drawing on resources at dangerous rates or exhausting the planet's reserves, a civilization could potentially utilize renewable energy on an astronomical scale, allowing for spectacular achievements in technology, infrastructure, and interstellar travel. Moreover, the search for extraterrestrial life often includes looking for signs of Dyson spheres or similar megastructures. If we could detect such massive constructions around distant stars, it would indicate that intelligent life is not only possible, but prevalent in the universe. The pursuit of this knowledge drives many researchers to explore our cosmic neighborhood, eager to unravel the mysteries of life beyond our planet and understand the energy-consuming practices of advanced civilizations. As astronomers peer into the depths of the cosmos, they are not just looking for planets, they are searching for signs of life beyond Earth. The discovery of exoplanets, planets orbiting stars outside our solar system, has ushered in a new era in the study of potential biosignatures. Biosignatures are indicators that suggest the presence of life, and the evidence supporting them often comes from a combination of atmospheric studies, spectral analysis, and chemical signatures. One of the most compelling pieces of evidence involves the detection of specific gases in the atmosphere of these distant worlds. For instance, a combination of gases like oxygen, methane, and carbon dioxide can indicate biological activity. On Earth, these gases coexist due to life forms that produce and consume them in a balance. When detected together in the atmosphere of an exoplanet, they provide tantalizing clues that life could be shaping those atmospheres similarly. Astronomers utilize powerful telescopes equipped with spectrometers to analyze light from the stars as it filters through an exoplanet's atmosphere, unveiling a chemical fingerprint that hints at organic processes. However, this search for biosignatures presents unique challenges to our definitions of life. Historically, we have defined life in terms of carbon-based organisms that thrive in conditions similar to ours. Yet, the universe may not abide by those narrow criteria. Researchers now ponder the possibility of non-carbon-based life forms or life existing in extreme environments that we have yet to explore. The very definition of what constitutes a biosignature may evolve as we gather more data from these exoplanets. As we expand our understanding of what life can be, we also expand the horizons of our cosmic quest. The ongoing exploration of exoplanets and their atmospheres beckons scientists to reconsider not only the conditions required for life, but also the very essence of life itself. Each new discovery challenges our assumptions, inviting curiosity and prompting us to reflect on the vast possibilities that lie beyond our small blue planet. It's an open-ended exploration into the great unknown, encouraging us all to think beyond our terrestrial experience. Microbial life thriving in extreme environments on Earth provides profound insights that shape our search for extraterrestrial life. From the steaming vents of the ocean floor to the icy expanses of Antarctica, these resilient organisms withstand conditions that would be inhospitable to most forms of life. Their existence suggests that life is adaptable and capable of surviving in environments previously thought unlivable, offering a broader definition of where we might find life beyond our planet. When we examine how extremophiles, organisms that thrive in extreme conditions, adapt to their surroundings, such as acidic lakes or deep-sea hydrothermal vents, we begin to appreciate the potential for similar life forms on other planets. For instance, the icy moons of Jupiter and Saturn, like Europa and Enceladus, harbor subsurface oceans beneath their frozen crusts. If these worlds possess the right chemical ingredients and energy sources, they could support life forms that resemble those found in Earth's most extreme habitats. Furthermore, the study of extremophiles also informs our exploration techniques. Understanding how microbes metabolize and adapt to extreme conditions helps scientists develop instruments and methods tailored for missions to Mars or distant moons. The factors that allow these life forms to survive, such as energy extraction from sulfur or even radiation resistance, guide astrobiologists in identifying biosignatures, chemical indicators of life we might detect in other environments. The study of microbial life in extreme environments not only broadens our conception of where life might exist, places we once deemed unworthy of exploration, but also enhances our ability to seek out those elusive signs of life across the cosmos. These insights spark a sense of wonder about the diversity of life, reminding us that we are just beginning to scratch the surface of understanding life's potential in the universe. The discovery of ancient microbial life on Mars would profoundly reshape our understanding of life's evolution, not just on our planet, but within the broader cosmos. First and foremost, it would suggest that life is not a unique phenomenon to Earth. Instead, it indicates that life could arise under similar conditions elsewhere in the universe, which expands the notion of where we might find life. This possibility raises exciting questions about the fundamental building blocks of life and the environmental conditions that foster its existence. Furthermore, if ancient microbial life were found, scientists would be eager to explore the lineage of that life and its relationship with Earth's organisms. Understanding how life evolved on Mars could provide vital insights into the processes that allow life to adapt and thrive in varying environments. For example, if the microorganisms on Mars share genetic similarities with Earth's early life forms, it would suggest a shared ancestry. This could imply that life on both planets may have originated from a common source, or perhaps life evolved independently but along similar pathways due to comparable atmospheric and geological factors. Another significant implication revolves around the resilience of life itself. Discovering evidence of microbial life that thrived on Mars millions or even billions of years ago would challenge our perceptions of life's limits. It might suggest that life is tenacious, capable of surviving extreme conditions that we previously thought were inhospitable. This resilience could also inspire new theories about life's potential to exist on other celestial bodies, such as the icy moons of Jupiter or Saturn, where conditions are thought to be similar to early Mars. In sum, finding ancient microbial life on Mars would not merely be an astronomical milestone, it would catalyze a paradigm shift in our understanding of life's origins, adaptability, and the very definition of what constitutes life in the universe. The implications extend far beyond Mars, inviting us to rethink our place in the cosmos and sparking the imagination about the myriad forms life might take throughout the universe. The vastness of the universe brings with it unique challenges in observation. Our instruments, while sophisticated, still have limitations that can hinder our direct understanding of cosmic phenomena. For instance, many events occur billions of light years away, and the light we receive from those distant realms is often faint or obscured by intervening matter. This makes it difficult to capture a complete picture of the universe and its sprawling complexities. As a result, scientists often find themselves relying on indirect evidence, which can lead to questions that remain unanswered. Given these observational challenges, scientists are inspired to explore speculative theories. When conventional methods fall short, the thirst for knowledge drives researchers to imagine what might be occurring beyond our sight. These theories, drawn from existing knowledge yet stretching into the unknown, allow scientists to propose new models of understanding. One notable example is dark matter, a theoretical substance that explains certain gravitational effects observed in galaxies, despite not being directly detectable. This area of speculative theory has become a significant focus in modern cosmology. Moreover, the interplay between observation and speculation works both ways. As new observations are made, they can either reinforce existing theories or challenge them, prompting innovative ideas. For instance, the discovery of exoplanets has fueled speculation about the conditions necessary for life beyond Earth. Each new finding can open up unforeseen avenues of thought, allowing scientists to theorize about not only the workings of the universe, but also its origins and possible futures. Ultimately, the limitations in our ability to observe the cosmos do not deter the quest for understanding. Rather, they enrich it. Speculative theories form a bridge between what is currently known and what lies beyond the reach of our instruments. They invite curiosity and creativity, ensuring that our exploration of the universe remains vibrant and ever-evolving. Through this blend of observation and imagination, humanity continues to push the boundaries of what we define as possible, always reaching outward into the cosmic unknown. Astrophysicists often find themselves at the crossroads of observation and theory when they encounter cosmic anomalies, strange or unexpected phenomena that don't quite fit into our established understanding of the universe. One of the biggest challenges is sifting through vast amounts of data from space missions, telescopes, and particle detectors. As they analyze these observations, they must interpret how these anomalies fit, or often clash, with existing theories like general relativity or our current models of cosmology. Take dark matter and dark energy, for example. While these concepts help explain a significant portion of the structure and expansion of the universe, the evidence we gather about them can be puzzling. When new anomalies emerge, such as unexpected gravitational effects or unaccounted energy distribution in galaxies, they compel scientists to reevaluate long-held beliefs. This is where the tension between evidence and established theories can create a complex landscape for researchers, as they must balance between modifying current models or even considering entirely new theories. Additionally, astrophysicists often grapple with limited observational access. Many cosmic events occur over vast distances or timescales, often beyond our observational reach. When a new anomaly presents itself, it may take years, if not decades, to gather enough data to understand its implications fully. For instance, the first detection of gravitational waves took years of meticulous preparation and data analysis to substantiate what might have seemed an outrageous prediction. Ultimately, the process of reconciling evidence from cosmic anomalies with existing theories embodies the essence of scientific inquiry, a relentless pursuit of understanding. Each breakthrough, whether it leads to confirmation or makes us rethink our models, is a step forward in our quest to decode the complexities of the universe. While the journey can be fraught with challenges, it also opens doors to exciting possibilities, deepening our appreciation of the cosmos and our place within it. Interdisciplinary research between astrophysics and quantum theory opens up exciting new avenues for understanding the universe. While astrophysics explores the grand scale of cosmic structures, such as galaxies and black holes, quantum theory delves into the fundamental particles and forces that govern their behavior. By merging these two fields, scientists can tackle some of the most profound questions about the nature of space and time, essentially bridging the vastness of the cosmos with the intricate world of the very small. One of the captivating areas where these disciplines intersect is in the study of black holes. Astrophysicists have established theories about their formation, structure, and effects on surrounding space. However, when quantum mechanics is introduced, it challenges our understanding of black holes, suggesting that information may not be lost inside them as previously thought, an idea known as the information paradox. This has spurred new theories, such as holographic principles, which propose that the universe might be a projection of information contained on a distant surface. Furthermore, quantum entanglement, a phenomenon where particles become interconnected in such a way that the state of one instantly influences the state of another, is inspiring innovative ideas about the fabric of the universe. Some researchers propose that entangled particles could be linked to the very structure of space-time itself. This notion is enticing because it suggests that, at a fundamental level, everything in the universe is interconnected, prompting us to rethink our understanding of reality itself. Finally, exploring dark matter and dark energy presents another fruitful overlap of these fields. While astrophysics reveals that these mysterious substances make up most of the universe, quantum theory provides hypothetical particles like axions as potential candidates for dark matter. By combining insights from both realms, we not only enhance our understanding of what lies out there, but also challenge and refine the theories that govern the underlying physics of our universe. This synthesis of knowledge holds the potential to unlock secrets about the origins, composition, and ultimate fate of the cosmos. Throughout the history of astronomy, our understanding of the universe has continually evolved, often leading to significant revisions of scientific models. One of the most striking instances occurred with the fundamental structure of our solar system. Initially, the geocentric model, which positioned Earth at the center of the universe, reigned supreme for centuries. This view was challenged by the heliocentric model proposed by Nicholas Copernicus, which posited that the Sun is at the center, with Earth and other planets orbiting around it. The observations made by Galileo Galilei, particularly of Jupiter's moons, helped to solidify this new framework, prompting a seismic shift in our understanding of celestial mechanics. Another remarkable example comes from our understanding of black holes. For many years, black holes were purely theoretical constructs based on Einstein's general theory of relativity. However, strong evidence for their existence gathered over time, especially with the discovery of the first known black hole, Cygnus X1, in the early 1960s. Later, the Event Horizon Telescope's capture of the black hole in the galaxy M87 in 2019 marked a significant moment in astronomy, allowing scientists to rewrite their models of cosmic evolution and the structure of galaxies, underscoring just how influential black holes are within the universe. The discovery of dark energy is yet another instance of a scientific model being revised. In the late 1990s, astronomers studying distant supernovae found that the universe is not simply expanding, but that this expansion is accelerating. This unexpected twist led to the formulation of dark energy, a mysterious force that makes up about 70% of the universe. As researchers continue to explore this phenomenon, they are faced with the challenge of integrating dark energy into the broader framework of cosmology, thus driving an ongoing evolution in our models of the universe. Lastly, the advent of exoplanetary discoveries has shifted our understanding of planetary systems and their formation. With thousands of exoplanets catalogued, many of which exist in conditions previously thought to be inhospitable, scientists are rethinking how we understand planet formation and the potential for life in the universe. This rapidly expanding field highlights our quest for knowledge and the willingness of the scientific community to adapt established models in light of new, sometimes surprising discoveries. Each of these moments underscores the dynamic nature of scientific inquiry, revealing how new findings can dramatically reshape our cosmic perspective. Technological advancements have always played a pivotal role in pushing the boundaries of our scientific understanding, particularly in the realm of physics. As we develop new tools and instruments, we gain the ability to explore and observe phenomena that were once beyond our grasp. For example, scientific instruments such as particle accelerators allow physicists to probe the fundamental building blocks of matter, revealing not only what exists, but also shaping our understanding of the forces that govern the cosmos. One of the most significant breakthroughs came from the development of advanced telescopes and satellite technology. With these tools, astronomers can detect distant galaxies, explore cosmic background radiation, and analyze the properties of black holes. Each discovery nudges us closer to understanding anomalies, such as dark matter and dark energy, which together comprise a substantial portion of our universe, yet remain elusive in their nature and behavior. These tools act as our eyes and ears in the vastness of space, revealing the intricacies of the universe while presenting further questions. Artificial intelligence also plays a growing role in driving exploration. It can sift through massive datasets much faster than any human could, identifying patterns and anomalies that may indicate new physics. For instance, algorithms have detected gravitational waves, a profound discovery that not only confirmed a prediction of Einstein's theories, but also opened a new avenue in astronomical observation. Thus, as we build smarter technologies, we increase our ability to question and investigate the very foundations of physical laws. These advancements create a continuous feedback loop. Each discovery leads to new questions and, in turn, inspires even more innovative technology. As we confront anomalies that challenge our understanding, such as the behaviors exhibited at subatomic levels or the mysterious forces at work in the cosmos, our evolving technology empowers us to explore these mysteries further, igniting a cycle of curiosity and discovery that fuels the quest for knowledge in the fascinating universe we inhabit. The discoveries of cosmic anomalies can reshape our understanding of the universe and our place within it. These anomalies often challenge existing theories in physics, opening doors to new knowledge about fundamental forces, the structure of space and time, and the very fabric of reality itself. By studying these unusual phenomena, scientists may gain insights into dark matter, dark energy, and the potential for different dimensions of existence. As we unravel these cosmic mysteries, there could be profound implications for humanity's future. For instance, if we find evidence of other intelligent life forms or alternate civilizations, it could redefine our understanding of life as we know it. This knowledge might inspire cooperative explorations or even initiate a new era of collaboration across nations as we collectively pursue answers to cosmic questions. On a more practical level, understanding cosmic anomalies could lead to advancements in technology and engineering. Breakthroughs in materials science or energy sources inspired by these discoveries could revolutionize space travel, making it possible for humans to journey beyond our solar system. Imagine a future where colonization of other planets becomes viable, driven by innovations that emerged from studying the universe's oddities. Ultimately, the exploration of cosmic anomalies not only feeds our innate curiosity, but may also provide humanity with tools and perspectives necessary for survival. As we deepen our knowledge of the cosmos, we may learn to anticipate challenges like asteroids or supernovae. Thus, our survival may hinge not just on understanding our planet, but on comprehending the grand tapestry of the universe where we find ourselves. Understanding dark matter and dark energy could revolutionize our approach to space exploration in profound ways. Currently, scientists estimate that dark matter constitutes about 27% of the universe, while dark energy makes up around 73%. These mysterious components dictate the universe's structure, expansion, and fate. Gaining insights into these forces could enable us to navigate space more efficiently and deepen our comprehension of cosmic phenomena. As we uncover more about dark matter, we may discover potential resources or phenomena that could be harvested or utilized during exploration missions. For instance, if dark matter interacts with regular matter in ways we have yet to fully comprehend, it could lead to new technologies that enhance propulsion systems or energy sources. Imagine spacecraft capable of harnessing dark matter's elusive properties, dramatically changing our travel capabilities and range within the cosmos. Furthermore, the role of dark energy in the accelerating universe could shape long-term exploration objectives. Understanding how dark energy affects the cosmos will help scientists predict the distant future of the universe and inform us about what kinds of environments exist far beyond our solar system. It may even guide us in identifying locations where conditions might be favorable for human existence or resource extraction. Ultimately, unraveling the mysteries of dark matter and dark energy could not only fuel scientific curiosity, but also provide practical benefits for humanity's future in space. It could enhance our technological progress, refine our exploratory missions, and perhaps even pave the way for interstellar journeying, opening up a universe ripe for exploration and understanding. Breakthrough discoveries in space often serve as catalysts for innovation here on Earth. When scientists embark on missions beyond our planet, they not only seek to answer fundamental questions about the universe, but also push the boundaries of what technology can achieve. For instance, advancements in satellite technology have revolutionized communication, weather forecasting, and global positioning systems, allowing us to navigate the world with incredible ease. Consider the development of materials designed to withstand the harsh conditions of space. These materials often find their way into everyday products, improving their durability and performance. For example, spacesuits are designed to protect astronauts from extreme temperatures and radiation. The technology behind these suits has inspired the creation of high-performance sports gear and fire-resistant materials for safety equipment. Moreover, the challenges of space exploration drive research into energy solutions. The pursuit of more efficient solar panels and energy storage systems not only aids space missions, but also helps address energy demands on Earth, promoting sustainability. The quest for understanding how life can exist in space leads to advancements in biotechnology, which can improve agricultural practices and medical technologies on our planet. Finally, the global collaboration inherent in space exploration fosters an environment of shared knowledge and innovation. As researchers from various countries come together to solve complex problems, the resulting technologies can lead to breakthroughs in fields like medicine and environmental science. Thus, the next time we look up at the stars, we can appreciate how our curiosity about the cosmos ignites ingenuity and progress here at home. As we venture deeper into space exploration, discussions about cosmic anomalies, those unusual and perplexing phenomena scattered across the universe, may profoundly influence our ethical considerations. These anomalies challenge our understanding of the cosmos and push the boundaries of what we know, prompting us to question not just our scientific practices, but also the moral implications of our actions in space. For instance, encounters with celestial bodies or signals that defy current theories may lead us to contemplate our responsibilities towards potential extraterrestrial entities. If we were to discover signs of life, whether microscopic or intelligent, it would raise profound ethical dilemmas about how we interact with these beings. The past has shown us how missteps in exploration can lead to catastrophic consequences for indigenous populations on Earth. This raises the question, how can we ensure that we do not repeat history when exploring the vast unknowns of space? Moreover, cosmic anomalies such as black holes or nearby supernova offer not just scientific intrigue, but existential reflections on humanity's place in the universe. They provoke thoughts about our survival, our long-term stewardship of not just our planet, but possibly other worlds as well. Ethical frameworks will need to evolve to accommodate these ideas as we grapple with concepts of preservation, exploration, and the potential impact of our activities on the larger cosmic environment. In conclusion, as cosmic anomalies inspire us to think beyond our current understanding, they will undoubtedly guide our ethical compass in space exploration. This fascinating interplay between curiosity and morality will shape not only how we explore, but also how we define our role in the universe as responsible descendants of Earth. The more we learn about the cosmic tapestry, the more we must consider how to engage with it ethically, ensuring we approach the unknown with both wonder and respect. As we look toward the future of space exploration, the potential for economic opportunities arising from deep space resource utilization is both exciting and promising. One of the standout prospects lies in mining asteroids. These celestial bodies are thought to contain a treasure trove of valuable materials, including metals like nickel, cobalt, and rare earth elements that are essential for technologies on Earth, from smartphones to renewable energy solutions. The feasibility of extracting these resources could not only decrease dependence on terrestrial mining, often a source of environmental concern, but also pave the way for an interplanetary economy. In addition to asteroid mining, the Moon presents another significant opportunity. With abundant helium-3 deposits, the Moon could serve as a source of fuel for future fusion energy advancements, offering a cleaner energy alternative. Establishing mining operations on the Moon could provide the necessary infrastructure and technology development that would ultimately lower costs and spur further ventures into deep space. Investing in lunar activities may also inspire a new sector focused on developing technologies for off-world construction and habitation, fueling various related industries back on Earth. Moreover, the concept of in situ resource utilization, which involves using local materials for life support and fuel production, further expands economic opportunities. For example, extracting water from the Moon or asteroids can support deeper space missions, reduce launch costs, and sustain long-term human presence in space. The technology developed for these processes could translate into advancements in recycling and resource management on our own planet, creating a ripple effect of benefits. Finally, the investments in deep space resource utilization can stimulate the growth of new industries and job markets, driving innovation in fields like robotics, artificial intelligence, and materials science. As private companies and governments alike step into the realm of space exploration, we stand on the cusp of a new economic era, one where the final frontier becomes a canvas for sustainable economic growth, scientific discovery, and technological advancement. In the vast realm of modern astronomy, numerous significant questions linger regarding cosmic anomalies, mysterious phenomena that challenge our understanding of the universe. One such question involves dark matter. We know that it exists because we can see its gravitational effects on visible matter, but what exactly is it? This elusive substance does not emit, absorb, or reflect light, making it incredibly difficult to study directly. Scientists are actively trying to pinpoint its nature, hypothesizing everything from exotic particles to potential links to yet undiscovered forces. Another profound mystery lies in the nature of dark energy, which is thought to be responsible for the accelerated expansion of the universe. While we can observe the effects of this cosmic force, including the observed redshift of distant galaxies, we have little understanding of its true nature. Questions abound. Is dark energy a constant, or could it vary across time and space? What role does it play in the ultimate fate of the universe? The answers to these questions could radically change our comprehension of the cosmos. Additionally, the existence of fast radio bursts poses another enigma. These brief yet powerful bursts of radio waves originate from galaxies far beyond our own, but their origins remain unclear. Are they the result of neutron stars interacting in unexpected ways? Or could they signify the presence of advanced extraterrestrial technologies? Each burst is like a cosmic riddle, inviting astronomers to decode its messages and understand the environments from which they emerge. Lastly, the question of life beyond Earth continues to captivate our imaginations. With the discovery of exoplanets outside our solar system, especially those within habitable zones, we wonder how many might harbor life. What conditions are necessary for life to thrive? And could we find it not just in our solar system but throughout the cosmos? As we pursue these compelling questions, they remind us of the vastness of our ignorance, urging us to explore, observe, and always seek deeper understanding of the universe we inhabit. Cultural perceptions of the universe profoundly impact how we engage with scientific discourse and exploration. Throughout history, Various civilizations have shaped their understanding of the cosmos through myths, stories, and religious beliefs. These narratives not only provided context for the vastness of space, but also influenced the direction of scientific inquiry. For instance, ancient civilizations viewed constellations as representations of gods and heroes, which guided their navigation and agricultural practices. Cultural lenses often frame the questions we ask about the universe, focusing exploration on aspects that resonate with human experience. As societies evolve, so too do their perceptions of the cosmos. In many cultures, the emergence of modern science marked a shift from mystical interpretations to empirical investigation. Yet, even today, remnants of cultural beliefs can influence how scientific findings are received. For example, discussions about extraterrestrial life are often colored by societal fears and hopes, shaping public opinion and funding priorities. In regions where religious views oppose the idea of cosmic evolution, scientists may face obstacles in promoting new theories, showcasing how cultural backgrounds can create divides in scientific acceptance. Moreover, these perceptions can foster collaboration and dialogue among diverse scientific communities. As researchers from different cultural backgrounds bring unique perspectives, they contribute to a more comprehensive exploration of the universe. For instance, indigenous knowledge systems often encompass deep understandings of astronomy, which can complement modern scientific approaches. This intersection enriches discussions about cosmic phenomena and encourages a more holistic understanding of our place in the universe. Ultimately, the interplay between cultural perceptions and scientific discourse serves to remind us that our quest for understanding is not just about cold, hard data. It is also about the stories we tell, the inquiries we pursue, and the ways in which we connect those cosmic mysteries to our shared humanity. This dynamic relationship helps shape not only scientific exploration, but also the very frameworks through which we interpret the world and our role within it. As we journey further into the vast expanse of the cosmos, we encounter not only scientific challenges, but also profound ethical dilemmas. One of the most pressing concerns is the question of responsibility. Who is accountable for the environmental impact of space exploration? Launching rockets and sending satellites into orbit may seem like feats of human achievement, but they contribute to pollution and the growing problem of space debris. As we expand our reach into the universe, we must consider the legacy we leave behind on both Earth and in space. Another ethical issue lies in the potential for extraterrestrial life. If we were to discover microbial life on another planet, for instance, would we have the right to alter that ecosystem for our own research purposes? This dilemma raises questions about our obligations as stewards of other worlds. Respecting the integrity of these extraterrestrial environments is crucial, especially if they host life forms that could be irreversibly harmed by human intervention. Additionally, the exploration of the cosmos invites us to reflect on our priorities here on Earth. With numerous challenges such as poverty, climate change, and global health crises, one could argue that our investments in space exploration should be redirected toward addressing these pressing issues. It presents a moral dilemma. Is it ethical to spend vast resources on cosmic expeditions while neglecting the needs of our planet's inhabitants? Finally, the technology developed for space exploration often leads to advances in other fields, but it also raises concerns about its dual uses. The potential for technologies intended for peaceful exploration to be repurposed for military applications poses a significant ethical question. As we advance our understanding of the universe, we must navigate these dilemmas carefully, ensuring that our quest for knowledge does not come at the expense of our ethical responsibilities. The quest to understand cosmic anomalies, those mysterious events and objects that don't quite fit into our current scientific frameworks, shapes our collective human identity in profound ways. These anomalies, from the perplexing behavior of certain stars to the strange movements of galaxies, force us to confront the limits of our knowledge. Every time we uncover something unexpected in the cosmos, we are reminded of how much there is yet to learn. This pursuit not only drives scientific innovation, but also inspires a sense of wonder and curiosity that unites us as a species. As we explore the universe's unknown corners, we often reflect on what it means to be human in the vastness of space. Cosmic anomalies challenge our place in the universe, urging us to consider whether we are isolated beings or part of a larger cosmic community. When scientists detect signs of an object behaving mysteriously, it triggers questions about the nature of reality itself. Are these anomalies evidence of phenomena that could alter our understanding of physics? Or could they even hint at forms of life or intelligence beyond our planet? Each exploration adds new layers to our identity, forming a rich tapestry of shared human inquiry. Moreover, the search for answers to cosmic anomalies encourages international collaboration. Scientists from different cultures and backgrounds come together, united by the goal of understanding the universe. This partnership reflects a broader human identity, one that transcends borders and emphasizes our shared curiosity about existence. Each breakthrough has the potential to reshape our narratives and expand our collective consciousness, as discoveries made in one corner of the world often resonate globally, impacting how we view ourselves and our future. Ultimately, the quest to understand cosmic anomalies shapes our identity by continuously challenging and expanding our horizons. In confronting the unknown, we learn about resilience and adaptability, precious traits that define the human spirit. As we reach for the stars and delve into the enigmas of the cosmos, we not only seek knowledge, but also forge a deeper connection to the universe we inhabit, making our journey a testament to our relentless pursuit of understanding. As we delve deeper into the unexplained realms of our universe, we encounter not only the thrill of discovery, but also a myriad of unknown risks. First, consider the very real possibility that our explorations could disrupt delicate cosmic balances. From altering the trajectories of asteroids to interference with the environments of other celestial bodies, our presence might provoke unintended consequences that could echo through space. Moreover, the risks extend beyond mere physical alterations. Encountering extraterrestrial forms of life, whether microbial or complex, poses profound questions and potential dangers. We could inadvertently introduce Earth-based organisms that might outcompete alien life forms, or worse, bring home pathogens that humanity has never encountered before. The unknown nature of these potential interactions leaves us at a crossroads in our pursuit of knowledge. Navigating the vastness of space also brings technological risks. As we send out more sophisticated spacecraft and probes, the complexity of systems increases. Communication failures, power issues, or even collisions with space debris can jeopardize missions and unravel years of investment in time and resources. Each mission carries the potential for significant loss and learning, reminding us that the universe is a challenging domain where even the best-laid plans can go awry. Lastly, the psychological impact of our cosmic exploration cannot be ignored. The vastness of the universe raises existential questions, provoking feelings of isolation or insignificance. For some, grappling with these thoughts may be overwhelming. Balancing the pursuit of knowledge with a responsible approach to our discoveries ensures that we remain not only explorers of the cosmos, but also thoughtful guardians of the environment and ourselves. In every step forward, we must weigh the risks against the wonders that await us in the endless expanse of space. The study of intergalactic space, the vast regions between galaxies, offers profound insights into the overall structure of the universe. This seemingly empty expanse is not devoid of interest. Instead, it holds crucial clues about how matter and energy are distributed on a cosmic scale. By examining the properties of these intergalactic regions, scientists can learn about the large-scale structure of the universe, including the formation and evolution of galaxies. Intergalactic space is permeated by very low-density gas, cosmic dust, and even dark matter. Together, these components create a web-like structure across the universe, often referred to as the cosmic web. This web consists of filaments of galaxies and clusters, separated by vast voids. Understanding the configuration of these filaments and voids helps astronomers determine how galaxies cluster and evolve over time. The arrangements we see today are shaped by gravitational forces over billions of years. Furthermore, studying the light from distant objects as it travels through intergalactic space allows scientists to learn about its composition and the physical processes that take place within it. For example, light emitted by quasars, which are incredibly bright and distant objects, can illuminate intergalactic hydrogen gas clouds along its path. Analyzing the changes in the light spectrum gives us information about the gas's temperature, density, and chemical composition. In addition, intergalactic space provides a unique environment to investigate dark matter, which makes up a significant portion of the universe's mass, yet remains invisible to direct observation. The gravitational influence of dark matter can be inferred from the movements of galaxies and galaxy clusters within this space. As our understanding of these relatively barren regions deepens, we unravel more of the universe's mysteries, revealing the intricate tapestry that connects all cosmic structures. The discovery of intergalactic clouds has profound implications for our understanding of the history of matter in the universe. These clouds, predominantly composed of gas and dust, exist in the vast spaces between galaxies and play a crucial role in the cosmic ecosystem. They serve as a vital reservoir of materials that can be drawn upon for the formation of new stars and galaxies, impacting the overall evolution of the universe. Historically, when the universe was much younger, most matter was concentrated within galaxies. Over time, as stars formed, lived their dynamic lives, and died, they expelled elements back into space. These expelled materials eventually coalesced into intergalactic clouds. Observing these clouds allows scientists to trace the journey of matter from stellar creation to its eventual distribution across the cosmos. This paints a picture of a universe that is neither static nor uniform, but an ever-evolving tapestry of cosmic material. Moreover, the composition and states of these clouds provide crucial insights into the state of the early universe. They are believed to contain primordial hydrogen and helium, remnants of the Big Bang, revealing the conditions that existed in those formative moments. Studying the chemical makeup of these clouds, scientists can infer more about the processes that led to galaxy formation and the subsequent recycling of elements through star processes. Finally, the presence of intergalactic clouds raises intriguing questions about the gravitational interactions and the dynamics of galaxy formation. It hints at a larger interconnectedness among cosmic structures, suggesting that galaxies are not isolated, but part of a complex web of matter and energy that shapes the universe. This interconnectedness invites us to revisit our models of cosmic evolution, offering a richer narrative about the life cycle of matter in the universe. Isotropy and homogeneity are fundamental concepts in cosmology, helping us understand the universe at its largest scales. To put it simply, isotropy means that the universe looks the same in all directions, while homogeneity indicates that it appears uniform when viewed from any point. These principles provide a foundational framework for models explaining the universe's large-scale structure, particularly in our observations of distant galaxies and cosmic radiation. When we observe the universe, especially at great distances, we notice a remarkable consistency. For instance, despite viewing millions of galaxies, their distribution follows patterns rather than random clumps. According to the cosmological principle, which is built upon the ideas of isotropy and homogeneity, this suggests that the universe is structured similarly no matter where you are looking from. This principle underpins many crucial aspects of cosmological theories, including the Big Bang model. One fascinating implication of these concepts is in the study of cosmic microwave background radiation. This faint glow, a remnant from the early universe, shows a remarkable uniformity around the sky. Tiny fluctuations in this radiation hint at the initial conditions that seeded the large-scale structure we observe today. Those fluctuations, while slight, were the seeds from which galaxies and clusters formed, showcasing the impact of isotropy and homogeneity on the grand tapestry of the cosmos. Ultimately, isotropy and homogeneity allow scientists to deploy sophisticated models like the lambda cold dark matter model to describe the universe's evolution. By assuming that on large scales, the universe is both uniform and isotropic, researchers can make predictions about its expansion and the distribution of matter. This understanding enhances our grasp of the universe's history and guides future explorations into its complexities and mysteries. Large-scale galaxy clusters are among the most fascinating structures in our universe, serving as key indicators of cosmic evolution. They are gravitationally bound groups of galaxies that can contain hundreds or even thousands of galaxies, along with immense amounts of hot gas and dark matter. Their existence raises intriguing questions about how the universe has evolved over billions of years. One of the primary mysteries is how these clusters form and develop over time. Current theories suggest that galaxy clusters originate from small density fluctuations in the early universe, which gradually grew as gravity pulled matter together. However, the exact processes that govern their formation, including the role of dark matter, remain elusive. Understanding the dynamics within these clusters can shed light on whether they evolve as isolated systems or as part of larger cosmic structures. Additionally, galaxy clusters provide insight into the distribution of dark matter. As much as 25% of our universe's mass-energy composition is believed to be dark matter, yet it does not emit light or energy and cannot be observed directly. By studying the gravitational effects within galaxy clusters, scientists can infer the presence and abundance of dark matter, which is critical for models of cosmic evolution. This understanding could lead to breakthroughs in unraveling the properties of dark energy as well. Finally, clusters of galaxies are laboratories for understanding cosmic history. By examining their various stages of evolution, astronomers can gather clues about the conditions in the early universe, the rate of cosmic expansion, and the impact of galaxy interactions over time. Each discovery not only enhances our knowledge about clusters themselves, but also contributes to a broader understanding of the universe's structure and fate, keeping the quest for cosmic knowledge alive and ever-evolving. Peculiar velocities of galaxies play a crucial role in our understanding of mass distribution throughout the universe. Unlike systemic velocities, which occur due to the expansion of space itself, peculiar velocities reflect the individual motions of galaxies in relation to the average motion of their cosmic neighbors. These unique speeds arise from gravitational interactions, whether from nearby galaxies, clusters, or even large-scale structures like cosmic filaments. By studying these velocities, scientists can infer how mass is distributed in various regions of the universe. One intriguing aspect of peculiar velocities is how they highlight the influence of dark matter. Observations show that galaxies often move in ways that cannot be fully explained by the visible mass around them. In regions where there seems to be a gravitational pull, like a galaxy cluster, peculiar velocities can indicate the presence of unseen mass. This correlation between the irregular motion of galaxies and regions of high mass concentration provides invaluable clues about dark matter's presence, which is thought to compose the majority of the universe's mass, yet remains largely undetectable. Further analysis of these peculiar velocities allows astronomers to map the underlying structure of the cosmos. By taking into account how galaxies move, one can create a detailed picture of both local and cosmic-scale mass distributions. For instance, the way galaxies cluster and interact with each other reveals gravitational wells filled with dark matter, leading scientists to understand not just where the mass is, but also how it influences the surrounding universe. In this way, peculiar velocities are much more than mere curiosities. They are vital components in the immense puzzle of cosmic structure. As researchers continuously refine their measurements and models, they unveil a richer picture of the universe's architecture, revealing the fascinating interplay between visible and invisible matter. This ongoing investigation invites us to ponder the celestial forces shaping our universe and our place within it. The concept of dark energy emerged from the surprising observation that the universe is not just expanding, but doing so at an accelerating pace. This finding was first revealed in the late 1990s when astronomers observed distant supernovae, or exploding stars. As they measured the light from these supernovae, they found that those furthest away were dimmer than expected. This dimness indicated that they were farther than anticipated, leading to the conclusion that the expansion of the universe is speeding up. One of the pieces of evidence supporting dark energy comes from the cosmic microwave background radiation. This radiation, a remnant from the early universe, provides a snapshot of the universe when it was just a fraction of a second old. Detailed measurements from satellite missions like the Wilkinson Microwave Anisotropy Probe and the Planck spacecraft have shown patterns in the temperature fluctuations of this radiation, which correspond to the density and composition of the universe. These measurements suggest that approximately 70% of the universe consists of dark energy, a force driving its accelerated expansion. Another key piece of evidence is the large-scale structure of the universe, including galaxy clusters. If gravity were the only force at play, we would expect the growth of these structures to occur much more slowly than what we observe. Instead, the distribution of galaxies and clusters shows that they are expanding rapidly. Dark energy, with its repulsive effect, helps explain why the universe's growth matches our observations rather than contradicts them. Lastly, gravitational lensing provides additional evidence for dark energy. This phenomenon occurs when the gravity of a massive object, like a galaxy, bends the light from objects behind it. Observations of clusters of galaxies reveal changes in their mass distribution over time, which aligns with the influence of dark energy. Each piece of evidence, from supernova observations to cosmic structure and gravitational lensing, weaves together into a larger picture that supports the theory of dark energy as the driving force behind the universe's accelerating expansion. Dark matter, a mysterious component of the universe, has sparked various theories that greatly influence how we understand gravitational interactions. Found in abundance, this invisible matter does not emit light or energy, which makes it challenging to detect directly. Instead, scientists infer its existence through its gravitational effects on visible matter, such as galaxies and clusters of galaxies. These interactions help shape the very structure of the universe. Different theories of dark matter range from the idea of cold dark matter, moving slowly compared to the speed of light, to warm and hot dark matter scenarios, where particles move more rapidly. The cold dark matter model aligns well with observed large-scale structures of the cosmos, explaining how galaxies form and cluster together. In contrast, warm and hot dark matter theories attempt to resolve some discrepancies in cosmic evolution. Each of these models presents unique implications for how gravity works on cosmic scales and offers insight into the density and distribution of matter in the universe. Furthermore, these varying theories challenge our understanding of gravity itself. For example, modifications to gravitational theory, like those proposed in modified Newtonian dynamics, suggest that at certain scales, gravity behaves differently than expected. This idea seeks to eliminate the need for dark matter altogether by adjusting our understanding of gravity, further complicating the narrative. Such debates drive scientists to explore new ways to test these theories, from particle physics to observational astronomy. The ongoing exploration of dark matter theories continually reshapes our understanding of gravitational interactions. As scientists strive to unravel this cosmic puzzle, each theory contributes to a broader comprehension of how the universe operates on both large and small scales. The quest to understand dark matter is as much a journey through the cosmos as it is through the foundations of physics itself. The nature of dark matter continues to be one of the most intriguing puzzles in modern cosmology. Although scientists have gathered a wealth of evidence suggesting that dark matter makes up about 26% of the universe, its exact composition remains shrouded in mystery. One of the core questions is, what is dark matter made of? Various candidates have been proposed, including weakly interacting massive particles, or WIMPs, and axions, but none have been definitively detected. Another perplexing issue is how dark matter interacts with normal matter. While we know it exerts gravitational effects, the lack of electromagnetic interaction means it does not emit, absorb, or reflect light. This makes it incredibly difficult to observe directly. Scientists wonder whether there might be interaction mechanisms that we have yet to discover or understand. What if dark matter interacts with itself in ways that could provide clues about its nature? These interactions could potentially lead to new physics beyond our current models. Additionally, there's an ongoing debate about the distribution of dark matter in galaxies and galaxy clusters. Observations suggest that dark matter does not conform to the same shapes as visible matter, leading to questions about how it's structured on cosmic scales. Some researchers are exploring whether dark matter is entirely uniform or if it has clumpy distributions that might affect galaxy formation and evolution in significant ways. These investigations are crucial, as understanding the distribution of dark matter could illuminate how it influenced the formation of our universe. Finally, scientists are intrigued by the possibility of how dark matter may relate to other forces in nature, including gravity. Could dark matter hold clues about the ultimate fate of the universe? As researchers continue to study the cosmic microwave background and scrutinize galaxy rotation curves, these questions remain at the forefront. The answers may redefine our understanding of the universe and lead us to new realms of knowledge, forever altering our perception of reality. Advancements in technology are poised to play a crucial role in deepening our understanding of dark energy, one of the most enigmatic forces in the universe. This mysterious energy is thought to make up about 70% of the cosmos, driving the accelerated expansion of the universe. To unravel its secrets, scientists are increasingly relying on sophisticated tools and innovative techniques, enhancing our capacity to probe the very fabric of space-time. One significant avenue of advancement is in telescopic technology. Modern telescopes, such as the Hubble Space Telescope and the recently launched James Webb Space Telescope, offer unprecedented clarity and detail. These instruments allow astronomers to observe distant galaxies and measure their redshifts with incredible precision. By understanding how galaxies move away from us, researchers can glean insights into the rate of cosmic expansion, which is tightly linked to the effects of dark energy. Moreover, advancements in computer simulations and data analysis are revolutionizing our understanding of cosmic phenomena. Sophisticated algorithms can analyze vast amounts of data collected from various celestial observations, revealing patterns and anomalies that may provide clues about dark energy. Machine learning, in particular, holds great promise, as it can identify and predict structures in the universe that traditional methods might overlook. Finally, upcoming projects such as the Euclid Space Mission and the Vera-C Rubin Observatory aim to produce immense surveys of the night sky. By tracking the positions and movements of billions of galaxies over time, these initiatives will provide a comprehensive map of the universe's expansion history. This wealth of data will empower scientists to test different theories about dark energy and potentially uncover new aspects of its nature, leading us closer to understanding one of the greatest mysteries of modern cosmology. The universe we inhabit is a fascinating and intricate tapestry woven from various threads of matter and energy. Among these, dark matter plays an often overlooked yet crucial role in cosmic development. Unlike ordinary matter, which makes up stars, planets, and even ourselves, dark matter does not emit, absorb, or reflect light. It remains essentially invisible, detectable only through its gravitational influence. This means that dark matter constitutes about 27% of the universe, overshadowing the ordinary matter, which accounts for merely 5%. As galaxies formed and evolved, the gravitational pull of dark matter provided the scaffolding that allowed ordinary matter to coalesce into the vast structures we observe today. Picture it like a cosmic web, where dark matter acts as the threads, creating gravitational hills around which gas and dust can gather. This pooling of ordinary matter led to the birth of stars and galaxies. Without dark matter, ordinary matter would scatter too widely, preventing the clumping necessary for forming the celestial bodies that populate our universe. Moreover, this interplay helps govern the large-scale structure of the cosmos. Dark matter influences how fast galaxies spin and how they come together to form clusters. Observations show that galaxies move faster than they should, given the amount of visible matter present. This is a clear indication of the hidden mass that is dark matter, exerting its gravitational power. Understanding this relationship is crucial for astrophysicists trying to piece together the puzzle of our universe's evolution, from the tiniest scales to the most massive structures. The mysteries of dark matter continue to fuel research and speculation. Scientists are constantly looking for more direct evidence of this elusive substance, pondering over its true nature. As we delve deeper into the cosmos, the interaction between dark matter and ordinary matter reveals not just how our universe has formed, but also how it might evolve in the future. The story of cosmic development is, in many ways, the story of these two types of matter coexisting and collaborating in a grand cosmic dance. As we gaze into the depths of the universe, we encounter some truly enigmatic phenomena that offer fascinating glimpses into the future of our cosmos. Dark matter and dark energy stand out among these mysteries. Together, they make up about 95% of the universe's total mass energy content. This invisible fabric shapes galaxies and influences their movements, yet it remains largely undetected, hinting that we have much to learn about the cosmos. By studying these phenomena, we can ascertain how the universe will likely evolve. Observations of supernovae and galaxy formation provide clues about the expansion of the universe, suggesting it is steadily accelerating due to dark energy. As galaxies drift farther apart, our universe teeters on the edge of fate, leading scientists to ponder whether it will expand forever, eventually turning cold and dark, or if it will reach a limit and begin to contract in a cosmic dance known as the Big Crunch. Additionally, phenomena such as black holes challenge our understanding of physics, particularly when it comes to the nature of time and space. The mysteries surrounding black holes could help us tackle some of the biggest questions in cosmology. Questions like what happens at their event horizons and how they might affect the fabric of the universe on a grand scale. By unlocking these secrets, we could gain insight into the ultimate fate of stars and the potential for new forms of matter and energy that could change everything we know. By meticulously studying these enigmatic elements, we are not merely seeking answers, but also expanding the boundaries of our cosmic understanding. With every mystery unraveled, we move closer to comprehending the universe's destiny, inviting us to reflect on our place within this grand tapestry of existence. The future of our universe is an ongoing story, filled with complexity and wonder, waiting for us to explore. As scientists delve deeper into the mysteries of the cosmos, they frequently stumble upon cosmic anomalies, those odd phenomena that challenge our current understanding of physics. These discoveries, whether they are strange objects, irregular behaviors, or unexpected signals from deep space, push the boundaries of established theories. When we encounter something peculiar, it acts like a puzzle piece that doesn't quite fit, prompting researchers to rethink the underlying principles of physics that govern our universe. For instance, consider black holes. Initially thought to be mere theoretical constructs, our growing understanding of them has illuminated various aspects of general relativity and quantum mechanics. When new observations suggest behavior that contradicts existing theories, like the potential for black holes to emit radiation, known as Hawking radiation, scientists are compelled to reconcile these discrepancies. This process can lead to groundbreaking theoretical developments or entirely new fields of study, sometimes referred to as new physics. Strange celestial entities like fast radio bursts or gravitational waves have similarly reshaped our understanding. These phenomena create unique challenges that expand our grasp of the cosmos. Each unexpected discovery acts as an avenue for exploration, leading to improvements in technology, new experimental techniques, and sometimes even entirely new branches of astrophysics. It emphasizes that our quest for knowledge is ongoing, and each anomaly teaches us something vital about the universe and, by extension, the fundamental laws of physics. Cosmic anomalies serve not only as mysteries to be solved, but also as beacons illuminating the road ahead in our scientific journey. They remind us that the universe is far more complex and nuanced than we might assume, encouraging a sense of humility and curiosity that fuels ongoing research and inspires future generations of scientists. Ultimately, as we uncover the nature of these anomalies, our understanding of reality itself may transform, revealing not only the workings of the cosmos, but also the foundational concepts of time, space, and matter. The exploration of cosmic mysteries is a grand endeavor that thrives on collaboration across international scientific communities. In a field as vast and complex as cosmology, no single institution or country can hope to answer all the profound questions that arise. By pooling their resources, knowledge, and expertise, scientists around the globe can tackle the mysteries of the universe more effectively. Each collaboration brings together diverse ideas and methodologies, enriching the overall understanding of cosmic phenomena. Many groundbreaking discoveries in astronomy and cosmology have emerged from international partnerships. For instance, the shared efforts of scientists from various nations brought us pivotal missions, like the Hubble Space Telescope and the more recent James Webb Space Telescope. These projects require enormous investments and diverse skill sets, yet they generate images and data that surpass what any single nation could achieve alone. Through this cooperation, researchers share the excitement and the challenges of their findings, fostering a spirit of unity and purpose. Furthermore, the complexities of cosmic research often call for specialized equipment and technology that are not universally available. By collaborating, countries can share the burdens of infrastructure costs and technological development. One prominent example is the International Space Station, where scientists can conduct experiments in microgravity that would be impossible on Earth. This global approach allows scientists to maximize their capabilities and resources, enabling them to explore cosmic mysteries that push the boundaries of our understanding. In the grand scheme, collaboration not only accelerates scientific discovery, but also fosters goodwill among nations. It cultivates an environment where minds from different backgrounds come together, united by a common goal: to understand our universe. As we continue our journey into the depths of space, the collaborative spirit of the global scientific community remains a cornerstone of our exploration efforts, leading to insights that resonate far beyond the laboratory and the observatory. The quest to understand cosmic anomalies captivates both the imagination and intellect of scientists and explorers, sparking a desire to uncover the mysteries of the universe. When we examine surprising phenomena like black holes, strange matter, or enigmatic bursts of radiation, we encounter puzzles that challenge our existing knowledge of physics and astronomy. This drive to understand the uncanny aspects of our cosmos encourages young minds to think critically and creatively, reminding them that curiosity is a powerful motivator in scientific exploration. These anomalies act as gateways to deeper learning, inspiring future generations to ask profound questions about the nature of reality. For example, once we witness the strange behaviors of black holes or the perplexing nature of dark matter, we ignite discussions about the fundamental laws that govern the universe. The stories of astronomers who have made groundbreaking discoveries, often based on unexpected findings, serve as a source of motivation for students dreaming of making their mark in the field of science. Furthermore, investigating cosmic anomalies fosters a spirit of collaboration and innovation across disciplines. Physicists, astronomers, and even engineers come together to decode these mysteries, showcasing the importance of teamwork in scientific endeavors. Young scientists are likely to feel inspired not only by the challenges presented by the unknown, but also by the cooperation and shared passion that characterize successful research teams, encouraging them to think about the value of collaboration in tackling complex problems. Ultimately, the allure of cosmic anomalies instills a sense of wonder about our place in the universe. Each discovery fuels the anticipation of what lies beyond our current understanding, creating a legacy of inquiry that extends far into the future. When young explorers witness the unfolding drama of our universe's secrets, they position themselves as the next generation of pioneers, eager to dive deeper into the cosmic ocean and explore realms yet undiscovered. This timeless quest for knowledge stands as a testament to the human spirit and our innate desire to understand the cosmos we inhabit. As we traverse the vast landscape of the unknown, both in science and in our everyday lives, a few guiding principles emerge that reflect the essence of exploration. First, there is the principle of curiosity. Science begins with questions, often fueled by an insatiable desire to understand the universe. This same curiosity sparks our personal journeys, driving us to seek deeper meaning and answers in our experiences. Embracing a curious mindset encourages us to engage with the world and to pursue knowledge without the fear of what we might uncover. Another key principle is resilience. In the realm of science, every theory and experiment opens the door to new questions, sometimes leading to unexpected results or failures. However, it is through these setbacks that breakthroughs occur. Similarly, in life, challenges often shape our path. When we face difficulties, it's resilience that empowers us to adapt, learn from our experiences, and continue on our journey, often leading to personal growth and transformation. Collaboration also stands out as a fundamental principle that shapes our journey through the unknown. In science, the greatest advancements often arise from teamwork, where diverse perspectives and expertise converge to tackle complex problems. This principle applies equally to life, where shared experiences and our relationships with others enrich our understanding of the world. Working together not only accelerates discovery, but also nurtures a sense of community and support. Finally, there is the importance of humility. In our quest for knowledge, we frequently encounter vast depths of complexity and uncertainty. Recognizing that there is always more to learn encourages an open mind and fosters an appreciation for perspectives that differ from our own. Whether tackling scientific mysteries or navigating the intricacies of life, embracing humility helps us remain grounded, aware that exploration is a lifelong journey filled with wonder, surprises, and endless possibilities.